Hi, I'm Suizet, digital nomad, web engineer, and wearer of hats. Today I'm going to teach you everything I know about mastering D3.js. I say everything, but that's a big word. Let's go for most. Either way, you're about to learn a lot of interesting things about D3.js, the web's most popular turn data into pictures library. And I say today, but you shouldn't rush. Take your time. If you ever have any questions, just shoot me an email or ping me on Twitter. I'm easy to find. I've designed this course with a simple idea in mind, to show you how to build a visualization from start to finish. We're going to build a visualization of all the UFO sightings in the United States that happened since the Second World War. Doing so, we'll go through everything from getting data, drawing maps, interacting with the user, animating things, and making sure our code works well and is structured so we're still going to understand it years from now. But before we do all that, we're going to look at layouts. The magic thing everyone's confused about because it makes pictures show up out of nowhere, but really it's just about reusable data transformation. Looking at code written with D3 layouts feels like looking at magic. Nothing is drawing a picture, but the picture still appears. It comes out of nowhere, with almost no code being used. But once you grok them, they actually make your code easier to understand. So why use layouts in the first place? You don't really need them. You could just as easily write all your code the way you always have, mixing the logic of calculating positions on the screen with the logic of drawing shapes. But that fast becomes messy. When you want to change the shapes something is drawn with, you're burdened with moving all the calculation and data transformation as well. It might not seem like a big deal, but it can be. Just think of the last time you had to refactor a piece of code that had magic values everywhere instead of keeping numbers in configuration variables. And that's where layouts come in. Their whole job is taking some data and transforming it into different data. Data that's easier to draw. That's it. That's all that layouts do. They're a simple function or a set of functions that take some data and transform it into the kind of data that fits the default value accessors of various path generators. The pie layout, for instance, helps you make a pie chart. A layout targeting rectangles would produce coordinates and widths and heights. One for arcs would create end angles and start angles, and so on. Anything we can do to make drawing easier. We're going to look at using layouts in more detail in the next video, but it's very easy in principle. You instantiate a layout, fill it with configuration parameters, give it some data, bind it to some shapes, and voila, a visualization. And that's it. That's how simple layouts make your code. We've gone through some of the basics of D3 layouts. We saw that they're not as magical as they seem, but transform data into other data. Easy. Next, we're going to create a pie chart manually and explore the challenges it offers. In this video, we're going to create a pie chart of UFO sightings by type. I found a cool dataset for us to play with, a list of UFO sightings going back to the late 18th century. We begin our exploration with a simple pie chart. Our pie chart is going to tell us the types of UFOs people are reporting. First, we're going to need the dataset. I've done the hard work for you and prepared a JSON file mapping UFO types to counts. Download it from the examples GitHub page and save it in your work directory. The pie chart begins with some basic HTML. We're going for the minimal HTML5 document with the doc type and a title. We're also going to use Bootstrap for our base styling needs, so we include the Bootstrap CSS. Having the div tag with class container gives us some nice padding around the edges. And we need a title and somewhere to place our graph. Finally, a bunch of script tags at the bottom of our HTML load jQuery, Bootstrap's JavaScript, D3.js, and our actual code. First, we'll need a drawing area. We use D3 to append an SVG element to our graph div. The actual size doesn't really matter because D3.js is vector-based. That means our image will be infinitely scalable, which is really nice. Then we use D3.json to load our JSON dataset and call the function we're about to define in the callback. Doing everything in data load callbacks is standard practice for D3 code. It ensures a quick initial page load for the user and sidesteps waiting for a DOM ready event. Next, we define the actual chart drawing function. We begin with the color scale, which we'll use to splash some color on the pie slices. The biggest color scale bundled with D3 has only got 20 colors, which is 8 less than we need, but we'll make do. It doesn't matter that much, as long as we can tell one slice from another.
We get the total sum of our data points with D3sum. We'll use this to decide how big slices should be. We're also going to need an offset function that calculates where a slice should go on the chart, and the easiest approach is to sum the sizes of all slices coming before a particular slice. And remember, angles are radians. An arc generator is going to build SVG path definitions for the slices. The offset function is perfect for giving the start angle, and we just add the size of a particular slice to the offset for the end angle. Creating a grouping element for every slice makes our lives easier in terms of positioning. If we make sure the grouping element is at the center of our pie, we don't have to worry about positioning the arc itself. I found this to be a much easier approach. Slice is now a D3 selection of grouping elements with all data points attached. From here we can append a path, tell it to become an arc, give it a color with fill, and add a title. The title will be used later to generate Bootstrap tooltips. If you run the code now, you'll see the pie chart looks kind of schizophrenic. The slices are all over the place and everything is just a mess. We can fix that by ordering our data. Back at the beginning of our drawing function, we just add a few lines of code to start the dataset by value. D3's descending function makes sure we correctly return -1, 0, and 1 to the sorting algorithm depending on the relation between two values. Our delicious pie looks much better, but it's impossible to tell what each slice represents. We can fix that by adding a tooltip. Bootstrap makes this possible with a simple function call at the bottom of our load callback. We just select all paths in the SVG element and add a tooltip. Remember to specify the container because you can't just add HTML elements all willy-nilly to SVG. Our chart works but isn't the best pie chart out there because we went through the slices in the same order we assigned colors. This creates funny-looking rainbow patterns and in some cases makes slices difficult to distinguish. This would be very difficult to fix. Another problem is that all our tooltips are on the right. It'd be nicer if slices on the left show their tooltip to the left, but we'd have to add extra classes to slices according to their angle. Also a pain and not the point of this example. We've gone through a simple pie chart example. Except it wasn't even that simple. I spent a surprising amount of time figuring out the best approach to calculating all those arc angles, and we still ended up with a lot of code. Too much code for a simple pie chart. In the next video, we're going to simplify this example with a layout.
In the previous video, we saw how cumbersome making something as simple as a pie chart can be. We're now going to make our lives easier with a layout. Regardless of how magical D3 might be, we still had to write a whole lot of code for a simple pie chart. Without a layout, D3 barely helped us beyond being an SVG manipulation library. We still had to do the heavy lifting ourselves. Maybe I don't do enough math these days, but I actually had to stop and think to figure out translating a value into a circle segment. And I got it wrong the first few times too. That probably says more about me than D3.js though. Add insult to injury, the final pie chart isn't even all that great on account of the funny looking rainbows. To start off, we're going to copy all the code from our manual drawing function into a new function. We're awesome enough that most of the code is going to end up looking exactly the same, just cleaner. Now we can remove the total calculation and the offset function. They're a mess, so you won't need them anymore. Instead, we define a default pie layout and tell it how to get value from our data with a value accessor. That's it as far as calculating slice positions and angles goes. All done. When binding data to a selection, we now have to call pie as a function of our data. And by the way, the idea behind data binding is that we attach each piece of data straight to the SVG element. This way it's always available right where we need it. Anyway, the layout creates new data objects with the correct angle properties. They will be picked up by the default arc generator data accessors. Another thing we have to fix is how we're defining the title for tooltips. Our dataset no longer lives at the root level of bound data, so we have to go through the .data property. Not a big deal. Running the code now gives us a much better looking pie layout. It's ordered the same as before, biggest to smallest slice, but the pie layout was smart enough to maintain original data ordering when traversing the list. This created a much better situation as far as colors go. There's no rainbows and the slices are easy to distinguish. The pie layout lets us tweak some settings as well. 3 to be precise: ordering, start angle, and end angle. We can define an ordering function, easiest is with D3 descending or ascending, but we could easily write a custom function to do something really weird. The start angle and end angle options let us define how the pie chart is oriented using radians. By default it starts from 0, but we can rotate it wherever we want. Notice none of this means changing the code in a significant way. I dare you to try playing around with this in our manual implementation. We took our manually implemented pie chart with all the cumbersome calculations and mucking about with things we don't really care about and made it clean using a layout. Our code became simpler and easier to understand. Separating the drawing logic from the logic of calculating positions on the canvas makes our lives easier, much like using CSS is easier than putting all styling in the HTML, or like we separate the controller from the view in MVC architectures. In the next video, we're going to look at some other layouts that came bundled with D3. Now that we saw how much easier drawing a pie chart is with a layout, let's take a look at some of the other layouts that come bundled with D3 by default. D3 comes with a bunch of layouts designed to help us with various simple charts and more complex visualizations. It can feel like the default layouts were picked almost at random, but most of them serve a use beyond the most obvious. For instance, I sometimes use the histogram layout as a general binning function, and the stack and partition layouts in particular can be used for a lot of different visualizations. We can split layouts roughly into two categories, normal layouts and hierarchical layouts. As you might have guessed, the normal layouts are perfect for playing with flat data like variable distributions or relation matrices, and hierarchical layouts work great for nested data such as graphs and trees. Of the regular layouts, we've already explored the pie layout when making a pie chart of UFO types, so we won't go into this one anymore. Another great layout is the histogram layout. Its primary use is showing distributions of variables in a bar chart. Think exploring how a random function behaves or seeing how startup exit valuations follow a power law. The histogram layout will magically handle numerical values by calculating appropriate bins on its own, putting values into the bins, everything. But with a bit of tweaking and playing around, you can get it working with ordinal values as well. That's when it stops being a histogram and becomes a regular old bar chart. We explored this idea in greater detail in one of the examples in my data visualization with D3.js book. You should check that out. There's also a layout for chord diagrams. Now, I never quite figured out how to make these look and feel intuitive, but apparently they're pretty popular in the genetics community. They're perfect for displaying how different nodes affect one another. Only time I ever found a use for this was creating a visualization that shows friendly relationships on an IRC channel based on who is giving karma to whom. It looked pretty, but I don't think anyone learned much from the experiment. The hardest part to grok is that both sides of each relationship are the out part. That is, one end of the chord shows you how much that side is affecting the other side, and on the other side it shows you how much that side is affecting the original side. Confusing, but so pretty. Has shown up on magazine covers. Stack is another versatile layout. You can use it for everything from stacked bar charts to string graphs. The trick is that it doesn't actually do much, it just calculates vertical baselines for rows in a matrix. Each new row gets positions on top of where the previous row ended. Then it's up to you to represent this as either a stacked bar chart using rectangles or a string graph using areas. Hierarchical layouts are a whole different ballgame. In a way, they're easier to use because all of them follow the basic layout very strictly, but there is still a large range of different outputs, so things can get tricky. For instance, there's a layout for drawing dendrograms, the cluster layout, and a layout for drawing trees. They both end up looking pretty much the same, except the cluster layout aligns leaf nodes in nice vertical clusters, and the tree layout arranges them in a circle. But you can't really use these two for much other than their primary purpose, at least as far as I know. Another great one is the tree map layout. I'm not sure why it's named that way because it doesn't create a map of trees, but it's a great layout for showing how big things break down into small things. You'd normally use it to create nested rectangles, for something like a budget distribution perhaps, or showing which team fits into which department. With this visualization, you are primarily exploring the relative size of nodes, similarly to the pack layout, which compares node sizes as circles but is less useful. I think pack is prettier though. My favorite of the hierarchical layouts is the partition layout. It does something similar to the tree map layout, show you how things are comprised of other things, but does so in a clearer fashion because there's no overlap. You'd use this, for instance, to create an icicle diagram where each successive layer shows you how the layer above it breaks down into different parts. And finally, everyone's favorite example of how magically awesome D3 is, the force layout. It's fairly useless for most occasions, but it looks really cool because it uses force simulations to draw a graph interconnected nodes. Nodes that have a stronger connection end up closer together and everything gravitates towards the center, which is pretty neat, I guess. But even though it shows up in all the books, I don't think I've ever seen this one used in the real world, at least not directly. We've gone through the layouts bundled with D3 and seen what they can do. I suggest exploring the API documentation on GitHub to figure out how to use them. It shouldn't be too hard. Don't forget to check out the plugins directory for even more layouts. You should know by now how great layouts are, how they can simplify your code, and that they aren't as scary as they first appear. But you only know how to use ones made by others. In the next section, we're going to look at making our own D3 layout with custom awesomeness and ease of use. Same UFO dataset, but we're going to care about time rather than shape. In this section, we're going to create a layout of our own, an angle histogram. We're going to start with a sketch and end up with a pretty example of our new layout. Before you can make a layout, you need a working visualization. A sketch makes it easier to play around with concepts to figure out what you actually want to build and whether it's even possible. So we're going to use the UFO dataset, just like we did in section 1, and this time we're going to play with the sightings per hour data. Arranging the histogram around a 24-hour clock looks better than a bar chart, I think. And making a specific example means you know your layout will be useful. We're going to start with a regular histogram, change its results to work with arcs, and finally copy our pie chart code to the drawing. Easy. First, we're going to need the dataset and prepare a simple environment to work in. Here's the dataset I prepared earlier, just like this was a cooking show. We'll look at using D3.js with random datasets in a later video, so for now just take this one. It lists all sightings of triangle-shaped UFOs going back some 40 years. Save it in the directory you're going to work from. We're also going to need a simple HTML file to hold everything in place, load our JavaScript files, and so on. Best bet is to just copy the one you used in the pie chart example and remove what you don't need. To start the JavaScript off, we set up an SVG drawing area and use D3.json to load our dataset. It's just an array of objects with some properties like the time of appearance, the state, the duration, city, and so on. One thing we do have to take care of are the timestamps. They're strings, but we'd like them to be date objects because that makes them easier to work with. We also want to ignore the entries without timestamps. Fixing this situation is simple. Go through data and parse every timestamp, filter out anything without a valid time, and make sure all times are date objects. We map through the data twice because date.parse gives us a timestamp and new date gives us a date object. I know, it'd make more sense if they were the same, but JavaScript. The best way to make a histogram of any shape, even a custom one, is starting off with the bundled histogram layout. This ensures we don't have to write our own binning code. I know it sounds simple, but it can get hairy, so it's best left as somebody else's problem. We define a value accessor that returns the hours part of every timestamp and ask for exactly 24 bins. Because there are 24 hours in the day. Running the histogram function gives us drawing data for a normal bar chart histogram. Tweaking it into a circle that's meant to be drawn with arcs instead of rectangles shouldn't be too difficult. We'll run through the data and add values that arc generators expect. A scale that maps values in the dataset to angles on a full circle will make it easier to define start and end angles. Scales are functions that map a domain to a range, by the way. Domain sets the from interval and range sets the to interval. Because we have a linear scale, the mappings are evenly distributed. We're going to make each value map to the middle of an arc by offsetting them by half the width. This makes the histogram look better because each slide sits right on top of its value. We also set a static inner radius and an outer radius which reuses whatever height the original histogram layout calculated for each bar. If you print the result, you'll see it's got everything we need. Each value holds the corresponding data points from our original dataset and all the metadata we need. We've essentially come up with a pie chart where slices don't have the same outer radius, but do have the same width. This means we can reuse our pie chart code from earlier to produce a crude drawing. We use the using layout function. Give it our data and remove all references to the pie layout because they're no longer needed. We can also get rid of titles and that outer radius setter. And there you go, a simple sketch of what we're aiming for. It's not the prettiest, but it does show that we know how to make an angle histogram. In the next video, we're going to generalize our code to make it reusable. Great, we've got our sketch of the angular histogram. Now let's make the code more reusable, then in the next video we're going to make the result actually look good. Once you have a working visualization, turning the relevant bits into a layout isn't too difficult. See that code where we add data to the histogram output? That's the part we're going to generalize and turn into a layout. To give it as much versatility as possible, we're also going to add some configuration functions. Our layout is going to be inspired by how the histogram and pie layouts work. You could say it's a combination of both. We're going to put our layout code in a new file called Angular histogram.js. And let's not forget to add it to the HTML like I did when I was coding this example. Just like other layouts, we're going to need a factory function that defines the actual layout function, its configuration accessors, and returns everything as a simple object. Making our layout inherit from the default histogram layout will make our lives easier, so the first thing our factory needs to do is get a histogram function, just like we did in our sketch code. Next, we copy-paste our sketch code into a new angle histogram function. Most of it is going to stay exactly the same for now. The only change we have to make is where we call the default histogram function. We have to play around with the scope and make sure to call the function on our local scope. This makes sure the histogram is going to use our configuration. If you aren't versed in JavaScript's dynamic scope shenanigans, you might want to Google for a few tutorials on .apply and .call. It's a bit mind-bending the first time around. Another thing we have to take care of is making sure all of histogram's accessors are available through our layout as well. We don't want to re-implement them because that's a waste of effort, and we want them to be available because our layout is a histogram as well. The approach is simple. We'll just loop through a list of function names we want to make available, wrap each in a function that applies the particular accessor on local scope, and return the angle histogram function again. All functions will be attached to the angle histogram object function under the same name. This might look tricky, but if you look at how these accessors are implemented in the default histogram, it makes sense. When the function is called, it either returns the current value or accessor function, or it changes the state of a variable inside the scope. By using .apply, we were able to trick those same functions to work with our object without re-implementing them. And because we use histogram.call as the basis of Angular histogram, things just work. Everything is running in our scope, even though it's defined in a completely different object. So we've basically tricked JavaScript into giving us object inheritance. The .apply calls are a bit like calling super, and always returning angle histogram ensures we can daisy chain methods when using them. Before we can make sure our layout acts the same as the sketch, we have to change some stuff in Code.js. Mostly we just have to remove everything we just copied into the new layout code and change what layout is being used. 3 simple changes: delete, change the call, and change what's fed into the using layout function. Refresh the page, and voila! Everything is exactly the same. How disappointing. But now that our code is kind of reusable, we get to make it versatile as well. We're going to do that by adding a few more functions similar to the ones we've stolen from the default histogram. First thing you'll notice is that our current Angular histogram is huge in a few places and tiny in others, to the point of being useless. We can't even fit everything on the page. So let's give users the ability to limit how high the histogram can go. But before diving into that can of worms, let's make the inner radius configurable. All it takes is a 5-line function inspired by the ones in the default layout. If there are no arguments, we return the current value of the inner radius variable. Otherwise, we override the variable with whatever the user has given us. Once we've got the function, we just have to move the static definition of inner radius inside the Angular histogram function to where we're going to define all other defaults. And we have to make sure that when we use it, we first check whether it needs to be called as a function or is just a value. Simple. Okay, now we can really get to the max radius stuff. But let's call it max height instead, because as I found after hours of fiddling, the API is easier to use when we don't try to take inner radius into account when limiting the height. The implication here is that max radius would say to a programmer that this is the biggest the whole graph can become, whereas max height is being added on top of inner radius. Is that as confusing as it sounds? Anyway, looking at the state of our graph, it's obvious we want the height to follow a logarithmic rather than linear scale. But not all data is going to behave the same. That's why we have to make sure users can either define a static max height or give us a scale to use. We copy the inner radius function and rename it to max height. Inside, the only difference is that we check whether the given argument is a function. If it is, we override the default value, otherwise we give the default scale a range. And on that topic, let's make sure the default for max height is a vanilla linear scale with no attributes defined. We do this at the top of the function with the other defaults. And without going into too much detail, we're relying on the fact that functions in JavaScript double as objects with properties. You should Google some guides if you think that's confusing. Now, to actually use the given max height, we have to make 2 changes to our code. First, we have to make sure we define the domain, which we can do as soon as the bins are calculated. Now, to actually use the given max height, we have to make two changes to our code. First, we have to make sure we define the domain, which we can do as soon as the bins are calculated. Before going into the loop that updates bins, we can use D3.max to find the maximum calculated height of our data. The domain for heights will go from 0 to max. Then we update the definition of outer radius to use the max height scale, and we're done. But the definition for the bottom of our domain is problematic. Given a logarithmic scale, the 0 will break things because log 0 is not a number. But if we satisfy the maths with a vanishingly small number, we break the relativity of the scale, especially for logarithmic scales because all values are a lot bigger than almost 0. The solution is to define a min height accessor. We set the default at 0 and write exactly the same accessor function as for the inner radius. All we have to do is copy-paste and change variable names. Then we go back to the max height domain definition to change the pesky 0 to the more flexible min height. Essentially, we just call it with the minimum value in our data, if it's a function, otherwise we can use it as a static value, and that's it. We should test what we've made so far. So let's go back into code.js and change a few things so they use max height and min height appropriately. We give max height a logarithmic scale with a defined range of heights, and min height gets a simple accessor that divides the smallest value by 2. To me, this created the most visually appealing and sensible results. But it does mean bar heights tell us how many times more than half the smallest value each value is, which could be difficult to grok for somebody who wants to get into the specifics, but works pretty well as a general overview of proportions. Since our layout is essentially a pie, we might want to add some of the configuration options from the default pie layout as well. Namely, the start angle and end angle accessors. This lets people make the angle histogram span less than a full circle. The approach is similar to before. We define a default start and end angle, then copy-paste the basic attribute accessor we've used before and change variable names. It's a shame we can't make a more generalized function for this that we could just ask to define a generic accessor, but I couldn't find a decent way of doing it other than having all values stored in a dictionary. But that feels kinda messy. So once we have the two angle accessors, we go back to the angle histogram function and make sure we use them. We call them if they're a function or use them as a value. Then we change the radians function range so it uses those values and we're done. Everything works. We've gone through the task of changing our one-off visualization code to a reusable and configurable layout. Granted, it's among the simplest layouts you can make, but the approach should apply everywhere. In the next video, we're going to make the example for our layout look better. Now that we've got a versatile layout for angle histograms, we have to make the example sketch look better. This code is meant for others to use, so we want to make a good impression. We made an angle histogram layout so that we can display our data around the clock. Data fills the whole day, so having it around the clock is going to look cool. But we need to add a clock face, and we should do something with the color scheme because right now it doesn't mean anything and just looks messy. We'll make colors represent the daily light cycle, because that just looks cool. First thing we're going to do is take care of those colors because that's the easiest. We just have to change the color 20B color scale to something that creates a nice gradient from night to sunrise to day to midday and back to night again. D3 is smart enough to blend colors and turn linear scales into gradients. Because we have multiple colors, we're going to use a polylinear scale. This will involve some manual tweaking to get just right. By the way, a polylinear scale behaves like a bunch of linear scales stuck one after the other. I googled a bunch of different images of sunsets and dawns, then used Photoshop to get the color codes. We need 5. Night, sunrise, day, midday, and sunset. They go in the range part of our scale. Day and night colors repeat twice. We define when these colors are used with the domain. The most readable approach is to use fractions with a denominator of 24, the number of hours in the day, and fiddle with numerators that represent hours. We'll need 7 of them. The hours I found work best are 3 AM, 5 AM, 8 AM, noon, 6 PM, 8 PM, and 10 PM. This ensures the interpolator we use to map through the colors will be able to produce a gradient everywhere. Now we just use the gradient scale and we're done. Making a clock face is not going to be as easy. It would have been great if we could just use a D3 axis like sensible human beings, but I found no decent way of making it circular. So we get to make one from scratch. Yes! But we only need to do 2 things, the ticks and the numbers, which shouldn't be too hard.
Let's first make some room by changing the max height and inner radius. With that done, let's do the numbers. We already got a selection of all slices, so all we have to do is add a text element and give it something to say, the value. We're going to use a plain SVG transform to move it into place. The angle we want to rotate the text to is defined as the middle between start angle and end angle of each data point. And we have to change radians into degrees. For the actual transform, we have to offset the angle by 90 degrees because text shows up horizontally and we want 0 to be straight up. We move the element to somewhere near the inner radius of our histogram and rotate it again by 90 degrees so it looks aligned to the edge of a circle. Telling SVG to anchor text at the middle makes sure each label's middle aligns with the middle of its slice. Now you can't see anything because we forgot to make our layout return the value. We can fix that in angle histogram. Adding ticks follows the exact same principle except we use line elements and we don't have to rotate by those final 90 degrees. Easy! If you refresh the page now, you'll notice our ticks are invisible and our labels are kind of small. But that's why we define those classes. To the CSS! We add a few lines of CSS in an empty file called style.css. Everything that's a label should have a slightly bigger font size and lines should be stroked, black and crisp. After making sure the CSS loads into the page, our example is done. We've now got a custom layout with a presentable example. Not only that, but we've also learned that most UFO sightings happen between 9 and 10 p.m. and that UFO activity is generally highest at night. But I do wonder why 8 a.m. and 2 p.m. are extremely low. Through this section, you've turned a funny-looking sketch into a full-blown layout with configurable accessors, great reusability, and a beautiful example. Congrats, you're awesome! In the next section, though, we're going to look at how one might use D3 to get the whole UFO dataset.
We've done a little something with UFO data. The angular histogram looked pretty good and so did the pie chart. But before we can take the concept further, we need the whole dataset in an easy-to-use form. The National UFO Reporting Center publishes all UFO reports they get from the public. Well, I hope they clean out the obvious hoaxes, but the rest should be there. It's a rich dataset, sometimes going back over 100 years. Each report is labeled with the time of an event, what type of UFO was seen, a short description, the city and state it happened in, and how long the event lasted for. In total, there are over 88,000 UFO sightings here. But all this data is trapped in HTML tables on some website. To try visualizing it, we have to bring it to our local machine and transform it into an easier format, hopefully with less incomplete entries. We're going to write a simple Python script to download the dataset. I know this is a course on D3.js and we're supposed to use JavaScript, but sometimes you just have to use the right tool for the job. And besides, browser security models throw a hissy fit when we try to download files from a third party. Or at least they do with the default remote access functions that D3.js gives us. Something about running on a different domain than the target, and the target not having set any cross-domain headers. But first we're going to need a reference index that lists everything we have to download. We'll use the state index for no reason other than it looked convenient. As you can see, it's just an HTML table with states, numbers of sightings, and links to the full data. Save the file locally and off we go. But first we're going to need a reference index that lists everything we have to download. We'll use the state index for no reason other than it looked convenient. As you can see, it's just an HTML table with states, numbers of sightings, and links to the full data. Save the file locally and off we go. For some reason, nufork includes a whole HTML document inside the header part of each file. Now this won't confuse the D3 parser we're using for the rest of our conversion, but both Python parsers I've tried, PyQuery and Beautiful Soup, get confused and pick up only this useless fragment. So we have to manually delete the part of the file before continuing. Now that that's done, we can start working on the Python script to download everything. I do feel cheeky putting Python in a JavaScript course, but we're only going to use some basics, and Python is so ubiquitous you should know some anyway. If you don't care for Python, feel free to download the raw dataset from my GitHub repository and skip to the video about parsing it using D3. You're going to need PyQuery to parse HTML and Slugify to generate sane file names. You can install both with pip. The general approach we're taking is simple. Parse table, loop through links, download each file, done. We use PyQuery to read the index file and turn it into a jQuery-like object. Then use a list comprehension to produce a list of tuples. Each holds the full URL and a state name. As you can see, we're using that D object just like it was jQuery or a D3 selection. The only caveat being we have to keep converting raw node objects into the fancy object. Now that we've got a list of links, we just have to loop through them all and download the files. We use URL lib.url retrieve to download the contents of a URL into a local file whose name we got by slugifying the state name. And to make our script rerunnable, we make sure to skip those states we already got a file for. Scraping can be a very fiddly process, so it pays off to have rerunnable scripts that can continue where they left off. For instance, because I have crappy internet, I had to sometimes download files manually because the script got stuck and wouldn't continue. And that's it. With a few simple lines of Python, we have the whole 60 megabytes of HTML stored locally in a data directory. In the next video, we're going to use D3.js to transform all this data into a clean 12 megabyte CSV file with about 88,000 lines. Now that we've got our dataset stored locally, it's time to convert all those HTML files into a single CSV file. Having a bunch of HTML is fine and all, but the dataset is about 60 megabytes large, spread over several files, and has a bunch of invalid data points. Dealing with those every time we want to visualize something would really suck, so it's best to clean them out. Using CSV will bring the file size down to some 12 megabytes and make the data easier to parse. Especially important because we're parsing it on every page load. And by the way, CSV files encode their data as comma-separated values. That's where the name comes from. We begin with the same HTML file as always, but we're going to add two more JavaScript libraries, async and filesaver. Since we aren't using a package management system like Bower or something, the easiest way to get them is straight from the GitHub pages. We'll use async to go through data asynchronously, and filesaver will help us turn the resulting CSV dataset into a downloadable file. As I found, there's no other way to output that much data without crashing the browser. And after we add the necessary script text to the HTML, we're done with this step. Now we can go into code.js and start working on a function to parse stateindex.html. We use this to identify which files to look at, just like we did in the Python script. D3.html fetches an HTML file from the server and parses it into a DOM fragment. DOM fragments are like the regular DOM, but representing a smaller piece of the page, or in our case, a piece of a completely different page. You might have heard of this before as a shadow DOM. We're going to use good old JavaScript DOM accessors in a parseIndex function to access the data stored within this fragment. Using array prototype map call lets us map through the node list object returned by fragment.querySelectorAll. If you look at the node list object returned by querySelector, you'll see it looks just like an array. But it doesn't inherit from the same base object and is missing the normal iteration functions. We could avoid this roundabout call with a normal for loop, but those are messy. We'll talk about sticking to functional conventions and the dynamic scoping magic of .call in the next video. Just trust me for now. We want to turn every tr node into an object with a state name, a count, and a link to the real data. We get those by using the raw DOM API to access both cells in a row. We've turned the HTML index into an easy-to-use array. Now we're going to map through it, fetch every state's HTML file, and parse it. Because downloading data is an asynchronous operation, we can't just use a regular map function. We need the async version. The great async library by Kaolan implements asynchronous versions of all the popular list manipulation functions. They behave the same as their regular counterparts, but work through callbacks instead of returns. This way you can explicitly tell map when you're done, even if you have to do things in the background. More importantly, the iterator is called multiple times in parallel. In the end, our transform data is going to land in the final callback. But let's implement fetch a state first, because it will parse a single state's HTML file. Just like before, we use d3.html to fetch a DOM fragment and do the heavy lifting inside the fetch callback. We'll need time formatters for the two different timestamps in our data, the time an event happened with date and hour, and the date it was posted. D3 comes with a set of tools for handling time, the most useful of which are time formatters. They convert to and from strings and data objects. You tell them what a timestamp looks like using a simple DSL, and they handle the rest. Calling a formatter with a data object will produce a string. Calling the formatter's parse function will turn a string into a data object. There are also functions for handling time intervals, getting specific times out of thin air, and rounding times, but we won't need those right now. We will need a reference to the current year though. The dataset uses 2-digit years and we'll have to fix some Y2K issues. Who knew that was still a thing? Once more, we map through a state's data using array prototype map call and get table rows using query selector all. Inside the iterator, we use query selector to get the cells, then go through a list of cell names to make the parsed object. In the end, we use those formatters from before to parse both time strings into date objects. If you look at the object returned by this function, you'll see it's nothing special. Just the text contents of each cell transformed straight into a dictionary, and date objects were the ones we parsed with time formatters. Now, it would have been more correct to use D3.map, but I find regular old objects to be just fine. D3map implements ECMAScript 6 maps, which are going to replace this sort of abuse of objects for structured data containers. Anyway, not all those rows have valid times. Filtering those out will make our life easier down the line. And adding another map through the data, we can fix the Y2K issues that crop up. We can't get this perfect, but changing everything with a year in the future to be 100 years ago should be good enough. In the end, we tell async that no error occurred and give it a transform data with the callback function. The final transform data ends up in async map's main callback. We're going to transform it into CSV and output the result as a file download. We'll use two time formatters again, this time to turn date objects back into strings, but we'll make sure to use 4-digit years to avoid future Y2K problems. Our data is an array of objects, each of which contains the real data in a .data property. Using a nested map lets us go through each data point and format the times back into strings. Then we use .reduce to flatten everything into a single list of data points, because CSV does not do nested data. Our data is now a list of objects where each represents a row in the final CSV. Using D3 CSV format, we turn it into a CSV string with labels neatly stored in the first row. This will tell us what each column means later when we have to parse it back into a JavaScript object to work with. Using filesaver.js, we turn this string into a downloadable file via a blob object. A blob object is HTML5's way of making file-like objects out of some data. If it helps, you can think of it as a collection of bytes with a file type header. Then filesaver does some magic to make this file downloadable from the browser. We could probably do it manually, but it's easier this way. I did try some other methods of getting the data, but they all crashed my browser. Printing to the console, outputting it in a text area, everything crashed. But filesaver works flawlessly. Great, we've now got all UFO sightings data in a text file on our hard drive. We'll use it in all future examples despite its large size. Now compressing it would bring the file size down to about 4 megabytes, which is still huge but not too bad. It's about the same size of a large GIF. To produce this dataset, we've explored various concepts like functional programming, time formatting, and parsing various files. For more data formats, I suggest looking at D3's API documentation. It can handle most common data variations natively. In the next video, we're going to take a closer look at dynamic scoping and functional style coding. Our code so far has adhered to functional principles which made it cleaner, easier to read, and more composable. But we never really explained why. You can safely skip this section if you're already used to functional coding, but I felt it was important to include because D3.js follows a very functional design. How awesome JavaScript may be, it's not a real functional language. We get none of the assurances a good compiler will give us, but with some vigilance we get to pretend. And if nobody working on our code breaks the implicit promises we make, everything is going to be just fine. Two assurances in particular would make our lives easier: knowing that our functions don't have side effects, and knowing the output of which function can be safely used as an input for other functions. Pure functional languages use immutability to assure the first. Without variables, if you want to change something, you have to create something new, which is confusing at first but really useful, because it makes sure that running a function with the same parameters twice will produce the same result. This is called referential transparency and is what we're going for every time we write a function. The assurance that functions will cleanly flow into one another is usually given by a type system. We can't have this in JavaScript without fundamentally changing the language, but TypeScript made a decent effort. We're just going to rely on gut feeling and avoiding cleverness. We might also have to throw in a few more checks than strictly necessary because we're doing part of the compiler's work. With that in mind, let's take another look at some of the data processing code we wrote earlier. The bit of code that cleans up states data is a good example. In what is essentially a single expression, we extract data from HTML, clean out incomplete data points, and fix Y2K issues. Can you spot what makes this a single expression? If we hide the inner functions, you'll see this code chains 3 transformations in a single expression: a map, a filter, and a map. Proponents of functional programming will tell you this is a declarative approach. Instead of telling our code how to do something, we said what we wanted. This happens a lot in D3.js, where you never explain how to draw a circle or how to draw some complex graph. You just say, I want a graph here now. It's supposed to look like this. And that looks and feels declarative, but I've never found it intuitive with the basic map, filter, and reduce functions. I don't know why. If you can think of a map as a what, that's awesome. It's really just a transformation that takes a collection and uses a helper function to create a new collection. Transformations are whats. Same goes for filter. It's a transformation that takes away items that don't fit a certain predicate. Also a what. Personally though, I find it easier to think of them as loops. A map is just a fancy way of making a loop that applies a function on a particular element and saves the result in the same spot. Similarly, you can write a filter using arrays and a loop. Transformation like this exists for every functional concept out there. That's because Turing machines, where iterative programming comes from, and recursive functions in lambda calculus, where functional programming comes from, are equal in strength. I'm not going to go into all the theory, but just believe me that no matter what you do on a computer, you won't be able to make the space of solvable problems any larger. Or rather, we haven't found a stronger way of writing programs in the last 50 or 60 years, so everyone is assuming there isn't one. Eventually they all turn out to be equal. But that's theoretical computer science, which while fun, won't help us draw prettier pictures in the browser. So why do we want to write code like this? Why force a language with none of the assurances of a pure functional language to act like one? Because it makes our code easier to read. Sure, loops might look simpler to a novice programmer or somebody who's used to that sort of thing, but take another look. You have to read the whole loop to know what it does. With the functional approach, you can immediately tell whether it's a map or a filter or something else entirely, because you can at least pretend there's no side effect. The loop approach relies on side effects. It needs to change something outside the loop in order to work. But using functional primitives, we contain all our computation within functions and never poke outside that scope. Yes, we still can, but we don't have to. And that makes it more likely that our code will follow referential transparency principles. Because we can clean up the code. With loops, your code is there and it's doing what it does. With functional primitives, all those anonymous functions we defined could be easily moved elsewhere. Just make them named functions, put them in a completely separate file, and bam, clean code. You even get to reuse them in other transformations. Because we can chain them. A follow-on from the previous point, but unlike the loops approach, we can chain several tiny transformations. Our data is transformed in one fell swoop, and we can always be sure we're not using half-transformed data by accident. This comes in handy when you have multiple people working on the same codebase. And finally, because every transformation is self-contained, you can use libraries such as async to make transformations asynchronous, something you'd be hard-pressed to do using loops. Great, now you know about the basics of using a functional approach to writing JavaScript. We've been using it so far, and we're not stopping. But I promised a quick brush up on JavaScript crazy scoping as well. JavaScript uses lexical scoping, which means variables and functions belong to the scope they were defined in. If you define a new variable inside a specific function, it will only exist inside that function and shadow any variables of the same name that were defined outside the function. That part's simple. But where it gets tricky is that you also have closures, which bind the lexical scope to a variable and allow you to pass it around. This means that the lexical scope where something was defined can be different to the lexical scope when it runs. A lot of fresh JavaScripters get hung up on this because seemingly out of nowhere, variables don't hold the same value they expect. But as long as you follow a functional approach and your functions rely only on their direct inputs and avoid side effects, you will never encounter this problem. Until you start poking at it. You'll remember we played around with scoping rules when making our Angular histogram layout. A lot of that code relied on giving access to variables inside the scope, through functions that are available outside the scope. And we even made some functions believe they belong to a different object than where they were defined. Let's explain that on a simpler example. In the data transformation code, we wanted to apply a map on a node list. But node lists don't have a map function because even though they act like arrays, they aren't actually arrays. To solve this problem, we took the map function from arrays prototype and called it on the HTML fragment we wanted to process. This made the map function think it belongs to the node list and run in its scope. In simpler terms, we manually defined the this variable that .map runs against. Now we could also have used .apply instead of .call. It does the same thing, but takes an array of arguments rather than a list. This comes in handy when you're passing all the arguments from a function call into another function and aren't exactly certain what they are. Now I personally try to avoid using .call and .apply too much because they sometimes make code difficult to follow, but it's good to keep them in mind. They're useful in a lot of situations. I hope that clears up any lingering doubts about taking a functional approach to JavaScript and sheds some light on JavaScript's funny scoping. For a more complete set of functional tools, I suggest using underscore or Lodash in your projects. They implement a lot of the common functions from functional languages that are still missing from JavaScript's standard library. Following this section, you've seen what goes into parsing a raw dataset and turning it into an easier-to-use format. We made a simple Python script to download the dataset, then abused our browser to do the heavy processing, and finally took a more theoretical look at the principles guiding us when coding. Fun! Now we're going to play with geography in the next section. Now that we've got our UFO dataset in an easier-to-use form, it's time to do something interesting. Making a map that shows where UFO sightings happen in the United States. A friend recently told me that Conway and White used a similar example in their Machine Learning for Hackers book, which means that I am particularly uncreative, or that the example is just smashing. Let's go with smashing. We are going to begin with nothing fancy, just a simple map of the US so we have somewhere to place our data in the next video. In the process, we're going to explore D3's geography library, different map projections, and take a quick peek at geo data formats. Let's begin. First, we're going to need our trusty old index.html file. As usual, this is where all the JavaScript and CSS are loaded, and we have that one div for the graph. On top of the usual D3 and Code.js, we've also added Q, topo.json, and Lodash. Lodash is a utility library that's got useful functional programming primitives. We'll mention it briefly at the end of last section. Topo.json is Bostock's library for handling geographical data. We're going to look into that in more detail in the last video of this section. And Q is Bostock's library that makes it easier to load multiple datasets. It makes sure we can define multiple loaders and get everything into a callback at once. It's very neat, you'll see. In Code.js, we start with the usual boilerplate of adding an SVG element and sizing it appropriately. Next, we need a geographical projection and a path generator to draw the map features. We chose the Albers USA projection because it was created specifically for drawing USA maps, which makes it perfect for our use case. At this point, we could wax poetically about projections for a while, but instead I'm just going to show you what different projections do once we have our map rendering. Scale and translate parameters tell the projection how to behave and need to be hand-tuned for each situation. You'll see them in action when we play around with different projections. The GeoPath generator is where all the hard work happens. It can take any feature or geometry object from GeoJSON and turn it into a drawable path. Anything from a point or multi-point to a feature collection. We're not going to go into what exactly all the different features are right now, but keep in mind that you can put multiple features or geometry objects together in a collection and draw them with the same path. This renders faster than drawing each object separately, but doesn't let you interact with each one individually. For now, we've just told the path generator to use our projection, and the rest will come when we're drawing. We have to map between feature IDs and state names ourselves because the topo.json file we're using to make our map doesn't have any metadata. Let's just set up an empty mapping for now and fill it in later when we can see what's going on. On that note, let's get the file. There are many sources of geographical data, and we'll talk about them in more detail in the last video of this section. We can use Bostock's us.json file for now. He uses it in every official D3.js example that draws a map of the US. Save it next to our files and we're good to go. To make our map, we first have to load the data. Because we'll add more data sources in the future, we're going to use Q even though we're only loading us.json. As mentioned, queue executes multiple asynchronous functions and returns the results in a single callback. We first add a grouping element for each state. It will hold the state's field color and name. And we had to use the topo.json library to get a list of GeoJSON features out of the more concise topo.json presentation in our file. Don't worry about this bit right now, because we'll look into it later. All it takes to draw state surfaces now is to use our path generator on the selection. And after adding some CSS to style.css, well, the map doesn't look like much. Adding the actual borders will fix those weird artifacts between states, and adding some labels will help us fill in that state ID map. We can draw state borders using a single path. The main difference from drawing the areas is that we use topo.json to create a mesh instead of a feature data. The path generator handles everything else. Adding labels is pretty straightforward as well. We add a text element to every grouping element in our state selection. We then print either an ID or a name depending on whether it's already in the mapping or not. To position labels in the center of their state, we use GeoPath's ability to calculate the center point of a geo feature called a centroid. This works well enough for the general case, but has some problems with funny state shapes on the East Coast. Now, before we can see the result, we have to add styling for borders and labels to style CSS. And voila, a map of the US. Well, we still need state names. The easiest way to fill it in is using a US map found online, unless you know all the states by heart, which I don't. To add a state, just add it to the dictionary that's used to create state ID map. ID is the key, state name is the value. Easy. Once you're done, all state labels show a name. And we're also going to use state ID map to connect the UFO dataset to states later on. Oh, and I promised to show you some other projections. For no obvious reason, here are Mercator, orthographic, and equirectangular. The science of projections is vast and we won't get into it, but I wanted to show you how easy changing projections was. You should check out D3's documentation to find more options. We've gone through the basics of handling geography in D3.js, drawing a map. In the next video, we're going to augment this map with our UFO dataset. Now that we've got a map, let's put it to use. We're going to turn it into a choropleth map using data from UFO sightings in the US over the past 100 years. To do this, we'll visualize them as dots. At the end of this video, we're going to end up with what is essentially a population map of the US. The more people there are, the more sightings we expect in a given location. Dot density is going to be so high on the East Coast that we won't even see the map. And on the other hand, the West Coast is going to clearly highlight the two population centers, LA and SF. This means that the absolute number of UFO sightings correlates well with population. Naturally, we'll make the dots part of the map more useful in the next video. But let's start with the choropleth part. Choropleth maps use color intensity to highlight statistical data in predefined regions of the map. In our case, it's going to show how many UFO sightings per capita happen in a particular state. Darker colors mean more sightings per capita, lighter are less. As you can see, Washington has the most sightings per capita, followed closely by Montana, Maine, Alaska, and Vermont, while Texas, New York, and most of the southern states are almost invisible. Compare that to a choropleth of absolute sightings, where you can see that most events actually happen in California. That's because choropleths are only good at showing densities, not absolute values. Normally, you'd use them to show values per area, so we might be misusing choropleths here. But UFO sightings have more to do with population than the size of a state. The density of sightings probably correlates well with population density. A more accurate choropleth, then, would show sighting density in relation to population density, but sightings per capita are a good enough approximation for us. The rest of this example is going to produce a fair bit of code, so let's start by organizing it better. We make a helpers.js file and move our state ID map into it. Then we make an object called prepare that we'll use for data munching functions as we go along. This will keep our main code looking polished. Back in code.js, we add 3 more datasets to the loading queue. See, I told you it would be useful to load datasets in a queue, even though we only had one. The queue library will take care of all the data being loaded by the time our drawing function executes. Because we're playing with multiple datasets now, it makes sense to put them in a data folder next to our other stuff. This makes our codebase better organized. We'll talk more about finding geographical data and statistics in the next video. For now, just hop over to my GitHub repository and download the files. Awesome. Now let's take a look at those prepare functions. They're going to merge the datasets from their raw JavaScript representations returned by D3.json into easier to use objects. We covered most of the ideas behind this in the previous section. We add the functions in helpers.js. Nothing super interesting is going to happen here. The filter UFOs function cleans up our main dataset so it doesn't contain any sightings that happened outside the US. They either don't have a state or aren't in the known states array. We could have done this in 2 steps, but we have a lot of data points and want to optimize the amount of searching through known states. The UFOs function is simpler. It groups sightings by state. And the states function turns our states hash into a proper D3 map object. The populations function looks more complex, but it's not that bad. We've got an array of arrays, rows and columns from a CSV file, and we want a D3 map object that maps state names to their population. Load-zip object function returns an object created from a list of keys and a list of values. Lowercase state names are going to be the keys, and objects mapping years to their respective population estimates are going to be the values. The final trick is that we had to remove dots from number strings before turning them into proper numbers because they confuse JavaScript's number conversion. Then we go back to code.js and use the functions to fix our data. Now we can color our map. First, we'll need to count sightings per state. We do that by looping through the values in our UFO hash and dividing the length of each array with its respective population number. This is where our earlier work in preparing the datasets really pays off. Next, we prepare a quantized scale for the counts. Quantized scales divide ranges into quantiles of equal size. In using color to encode quantiles, you shouldn't use too many because it looks confusing. 5 or 7 is usually recommended, but 9 looked best when I was playing around with this example. The scale is going to return a CSS class name for each quantile. Then we make the state's drawing code use the quantile scale to add a class to each path. I also removed the labels to make the map prettier, but you can leave them on. After adding some classes to the CSS, our choropleth map will be complete. I strongly advise you to copy-paste this straight from my GitHub rather than typing it out. You will go insane. I should know, I painstakingly typed this out by hand because Color Brewer doesn't support copy-paste very well. And by the way, Color Brewer is a great place to get nice color schemes, especially for choropleth maps. Great, we've made a choropleth map of UFO sightings in the US. Ain't that dandy? Next up, dots for every sighting. We've already added the full geo-enriched data to the loading queue and prepared it with our prepare functions. All that's left to do is a glorified loop through the data that adds a tiny circle for each sighting. We add a grouping element full of circles, feed it an array of positions calculated from the projection, and make sure every circle is positioned correctly using its CX and CY properties. Then we add a few lines to style CSS and bam! Done! Because of our dataset size, the browser will take a few seconds to render the map, but you should end up with a map of every UFO sighting in the past 100 years. Or rather, a glorified population map. We've got some data on a map now. Great! But through this video, we've glossed over some important details, namely, where does all this geodata come from, what does it look like, and how on earth can we change our results so it's not just a population map. All this and more in the next video. In the previous 2 videos, we cared only about making a pretty map and glossed over some important details about the data. Our map also correlated strongly with population and wasn't very informative. Let's look at how geodata works, where it comes from, and how we can improve the map to make it more informative. Every good map needs 2 types of data, the geographical features and the metadata. You use the first to draw the map itself. Think back to when we were drawing a map of the United States. We loaded a us.json, then used the transformation from the topo.json package before feeding the data into a geographical path generator. That made a map. When we started placing useful data on top of the map, we relied on the second type of geographical data, the metadata. This essentially binds data onto the map. Geographical features usually come in one of 2 formats, GeoJSON or topo.json. with GeoJSON being the more widely accepted standard. As you can imagine, there's nothing special going on. GeoJSON is just a collection of JSON objects encoding geometries ranging from points to polygons using pairs of coordinates. It also supports so-called multi-geometries, where for instance you can have a multi-point which looks a lot like a line string, except the rendering system will draw multiple points instead of lines. Simple. Topo.json is an alternative format with growing popularity because it encodes whole features instead of geometries. As such, it tends to produce smaller files, which are also easier for people to understand. If you look at the code we use to transform Topo.json into GeoJSON, you can see how the improved structure of Topo.json helped us understand what's going on. We had a root node called US with a collection of objects, some of which are states. The collection of states contained all the features needed to produce state polygons, and using a different Topo.json function later on, including borders. Those were line strings. Compare this to the GeoJSON we produced, which is just a blob of geometry. There are many ways to get this data, but one of the easiest is to look for an official D3.js example that features the part of the world you want to show and borrow its Topo.json files. If you need something more detailed, I found Natural Earth to be a good resource while writing my book. However, when working on the examples for that book, I've often found the data too detailed. As a result, performance was poor and maps took a while to render. You can also look for GIS databases online. They have very detailed data that you can export to GeoJSON. If you're not worried about Google's copyright and rate limit policies, Google Maps also has an export to GeoJSON function in their JavaScript API. Once you have the features data, you can draw a pretty map. But figuring out how your data fits on the map could be a problem. Projection functions translate latitude and longitude into image coordinates, but most datasets don't include that data. A lot of datasets don't even tie into locations. These are useless in our case. Unless of course you can find some way to tie them to a dataset that does include locations, but that sounds more like data mining than data visualization, so let's not go there. When a dataset does have any sort of geodata attached, you're in luck. Even something as simple as a place name or a rough description of a location can help. If you have clean place name data, you can use GeoNames. It's a great database where more and more countries, cities, towns, and even buildings are annotated with their latitude and longitude. There's even an API, but a lot of descriptors in our UFO dataset were approximate. Things like street corners, places next to named locations, and so on. This makes things trickier, but it can be done with the right API. At this point, you have two choices: Google Maps or Bing Maps. I don't know which is more accurate, but Bing Maps lets you do a couple thousand requests per day after signing up for free, while Google Maps wants you to call their sales department for anything useful. To make the geocoded dataset we used in the previous video, I wrote a simple Python script that went through all the data and pulled the Bing Maps API for each data point, then wrote it all out into a CSV file for us to use. It relies on a cool library called GeoPy, which knows how to talk to Google Maps, Bing Maps, and a bunch of others. It even supports GeoNames, which is much easier than figuring out how to talk to all of those on your own. I won't go into too much detail about this script because it's really simple. The script will open an input and output file, skip the input file to find the last known row, then ask Bing Maps for a location of every row, save it, and that's it. That's all there is. The script serializes its progress, which allows it to resume from its most recent state in case your computer shuts down or something else gets in the way. You should always make sure your long-running scripts are rerunnable. It took a few days to go through the whole dataset, but it was worth it. We made a population map. We've run into a problem Randall Munro pointed out in XKCD a few years ago. Despite our best intentions, we've got a population map. That's because more UFO sightings happen where there are more people. To fix our map, we have to normalize all those sightings by population. But in a sense, they already are. One reported sighting per person. If we want to have any chance of a reasonable result, we have to cluster sightings into sensible units, preferably based on geography. There are a couple of approaches we can use: counting UFOs per county, city, or using various clustering algorithms. But while county population data is easy to find on census.gov, Their geographical boundaries are harder, and calculating which county a dot falls into is harder still. We'd essentially need a collision detection algorithm much like those used in games. Clustering by cities is difficult because you need a way to normalize place names. Some people say New York City, others say Bronx, and so on, and yet both of those are in the same city. The only real approach we're left with is clustering based on calculated coordinates. We want to put sightings that happen close together into the same group and figure things out later. Hierarchical clustering is a good approach, but we have too much data and every implementation I could find would run out of memory on my computer. It's a pretty intense algorithm to run on some 70,000 data points. K-means, instead, proved much more practical. It isn't as accurate as hierarchical clustering in some ways, but it's so fast we can run it every time we load the map. Although it would make more sense to save the results somewhere, but let's keep things simple. You can look up how K-means works online, but the gist of it is that given a set of cluster centroids, it will move those centers on every step in such a way that they will eventually come to the nearest densest spot on the map. Once they stop moving, the algorithm is done. Every spot belongs to its closest centroid to form a cluster. Now luckily someone's created an open source K-means implementation in JavaScript called Figure.js. We'll use this to find 120 clusters of UFO sightings before placing a circle on the map for each cluster. Using the Figure library and some census data, we're going to create a normalized map of UFO sightings. We'll finally have an informative map! But before we begin, you need the census data. You can get it straight from census.gov, but it's got a fairly involved API, and getting info for the various towns and cities in our dataset would take a while, especially considering the few providers of slightly nicer to use APIs have strong limits on how many requests you can make. Luckily though, UN data is an even better resource. It has global population data and offers direct downloads for its entire dataset. Download the city populations dataset and save it to your /data directory. When that's done, we add it to the list of datasets our map loads. Now we can add the clustering code in front of the section that draws UFO dots. Actually, we just have to make a few function calls. We'll add the meat of the logic into the helpers file. Clustered UFOs will return a collection of clusters, an array of labeled sightings tagged with clusters. Cluster populations will sum up the total population in every cluster. In helpers.js, the clustered UFOs function looks scary, but it's not that bad. In the first part, we filled a labels and a vectors array with values because that's what the Figure library wants from us. Labels is a way to identify data points and vectors is a list of positions. Then we ask Figure to do its magic and produce 120 clusters. When that's done, we use .groupBy to make a dictionary of clusters and labeled sightings. Easy! The cluster population function goes through the objects from previous examples. It shouldn't be too hard to understand. All that happens here is we first add population data from city populations to our cluster data, then make sure each cluster only contains unique cities, and we sum their populations. In theory, this will tell us how many people live inside each cluster Figure found for us. Back in Code.js, we can now calculate sightings per population. Nothing too fancy. Just go through the cluster data, get calculated population, and return the ratio. The scale is simple as well. It maps the domain of everything our data covers to a 2 to 20 range. Now we can change the drawing code to use this new data. Instead of feeding positions to .data, we feed cluster centroids, and instead of radius being a number, we use the scale we defined earlier. If we run the code now, we get a much improved map. Instead of a bunch of dots covering everything, we've got just the 120 circles representing each cluster, and their sizes depict sightings per capita. Something even more interesting shows up if we add Navy and Air Force bases as well. I got this idea and data source from a guy on Imager. If you look at the white blue crosses, you'll notice most, if not all of them, appear surprisingly close to cluster centroids, and the bigger the circle, the more bases there are in vicinity. This would indicate that most unidentified flying objects are actually military aircraft, either known or top secret. Or rather, if there's more things flying around in the sky, there's a larger possibility of some of them not being identified. Pretty cool if you ask me. Let's recap. In this section, we've finally done something cool and useful with our UFO dataset.
discovered that sightings happen near military bases. To do that, we first made a map of the US, painted it as a chloroplath, added points for every sighting, then played around with the data to make sure there was more going on than just where people live. In the next section, we're going to look at animations and making things move. Fun!
Maps with data are great and all, but we can do oh so much more. Animations! But our code has gotten big and messy. I can hardly see what's going on anymore, and animations are only going to make it worse. So we're going to do some housekeeping to get ready, then we'll jump headfirst into animating with timers. You can skip this video if you wish, but I'm going to assume you've gone through these steps. First, you need to copy the section 4 directory to a new one called section 5. Or not, you can continue from the same files. We're mostly going to poke at the draw function because it's overwhelming, and we're only going to make it worse. I suggest moving most of the drawing code into a separate function that's inside a drawers.js file. Inside drawers.js, we make a function that returns an object full of functions for drawing. This way we can define some common variables in the main scope, which means there are less arguments to pass every time we call a drawing function. First, we extract the map drawing code. That's everything to do with drawing a map, counting the UFOs, making a quantized scale, and finally drawing the map itself. The only change we made, other than grouping everything into a function, was that path is now geopath. This will make the code more readable because it's easier to guess what happens when you call drawers.map than seeing a blob of stuff. Next is the code for drawing Air Force and Navy bases. We didn't really go through this bit in the earlier videos, but there isn't much to say. You go through the bases, append a symbol for every base, and move it into position. That's it. And finally, the centroid function is going to draw all those cluster centroids. This function could do with some structuring of its own, but we won't poke around that much, so I'm not sure it matters. You have to strike a balance between beautiful code and getting things done at some point. For instance, both the centroid and map drawing functions calculate UFO counts per population. We could extract this into a reusable function that takes a list of UFO and population mappings and returns a result with the same mapping, but this will do for now. In Code.js, we can now replace most of the code with just 4 function calls. And to make the code even clearer, we rename path and projection to geopath and geoprojection. But to have a working visualization, we shouldn't forget to add drawers.js to the list of loaded scripts. Running the code now should give us the same result we got before the changes. Woohoo! We didn't break anything! Very well then. We've done the housekeeping chores and our code is as pure as morning dew. Time to start animating. Great, we've cleaned up the code. Time to start messing it up again and waxing poetic about how great animations are. Not only do animations look snazzy, they're a great way to explore the temporal dimension of a dataset. They're also paramount to user interactivity, but that's the next section. In this section, we're going to explore when all those sightings happen. The plan is to make an animated timeline with some text saying what year it is, and then having the sightings from that year showing up. While doing this, we're going to solve one major challenge and a few smaller ones, namely how to pack that much data into a sensible animation lag, and how to make sure the visualization makes sense the whole time that the animation runs. For instance, you wouldn't want to make a population map that then suddenly becomes normalized and correct in the last frame. That would just look silly. Throughout the section, we're going to use 2 basic ways to animate: timers and transitions. Timers are the harder way to animate because on every tick of the animation you have to manually define what happens, whereas with transitions you just define the start states, end state, and how long you want the transition to be. Usually you'd look at transitions first because they're simpler, but our example flows better the other way around. We're going to make a timeline animation of all the sightings, but there's about 50,000 of them. If we were to display one at a time, it would take almost 1,000 seconds of animation at the standard 60 frames per second. That's 13 minutes, which is far too long for the internet. Grouping by weeks and showing 60 of those a second would mean about a year a second, which would make a 1-minute long animation. But some years have 1,000 sightings a week, which would make it difficult to see at those speeds. The compromise I decided to go with is making every keyframe a season, showing a season a second, and displaying the innards of each season in sequence rather than all at once. In theory, this should create a smooth animation with a sensible scale. And since it comes out to only a few minutes long, it's almost short enough. The first thing we need is a helper function that groups UFOs by season. We add it to helpers.js. An ordinal scale helps us convert month numbers into seasons, and we use a combination of D3's time functions and the default date object stuff to generate year season keys for grouping. The result is a giant array of seasons where each entry contains a list of sightings that happened in that season. Simple. Back in code.js, we now make the main animation loop that steps through the seasons 1 per second. We can use a simple set interval. First, we use the function we just defined to get a list of UFOs grouped by seasons and made a new season scale. By now, we've realized that seasons are just a modulus by 4 of month numbers, so we can type less. Anyway, the fun part is the stepper. Set interval will call our function every 1000 milliseconds, or every second. But we wrap the actual timeline step function in a closure and open it up with a single function. This way we can keep account of how many times the function has been called without using global variables, which is one of my favorite tricks. Now we need that timeline step function, which we'll put right after the stepper code. As you can see, it's pretty straightforward. We use the season scale and a modulus to get the season, then we write out season and year to a title tag. Towards the end of the function, we check whether to advance the year or not, and make sure to clear interval when we're done with the dataset. Nothing special, but we use request animation frame to call the place UFOs drawing function. This helps us make smoother animations. You can look the details up online, but the gist of it is that request animation frame hooks into the browser's normal animation drawing loop, which in theory syncs it to your screen's refresh rate. If animations are going at 60 frames per second, that means you have a chance to draw something every 16.6 milliseconds. You will never catch this window by accident because your processing code just happens to take that long. Either it will be too fast or too slow, but the end result is always going to be the same: choppy animation. Browsers can also use various hardware acceleration techniques when you're playing nice with their native refresh cycle and so on. End of story is, do use request animation frame. Oh, and we shouldn't forget to add that h1 tag to our HTML. And now it's time to place the UFOs on every keyframe of the main animation. We go into drawers.js and make a new function called place UFOs. It takes a list of UFOs to put on the map, and that's all it cares about. The first version of this function is going to be simple. We're just proving the general idea that showing UFOs by season makes sense. All this function does is use geoprojection to get a list of positions, then adds a circle to the map for every sighting in the current batch. Simple. Let's see it in action. As you can see, it starts off slow, just 1 or 2 sightings per season, and it's difficult to see where they happen because they just appear. If you wait long enough, you'll notice that sightings become progressively more frequent as time goes on, and absolutely explode when the internet becomes popular around year 2000. I guess it's easier to report a sighting online than however NuFork accepted reports before. When it does explode, following what's going on becomes impossible. We can improve the animation by only drawing one sighting at a time and turning every season into an animation of its own. Instead of relying on set interval or set timeout, we're going to use D3's built-in animation timers. First, we have to make sure sightings are ordered by time. We do this using Loadash's sortBy function, which lets us specify a function as a sorting parameter. Once the positions are sorted by time, we initially draw all the sightings as invisible, and we're going to make them appear inside a D3 timer callback. D3's built-in timers rely on the same principles we did when using setInterval a few minutes ago. It's going to repeatedly call our function until we tell it to stop. The timer is going to call our function on every loop of the animation refresh cycle to give us the best approximation of 60 frames per second, either by using a request animation frame, if available, or by guessing the most appropriate timing interval. We can also give it a delay and a time if we don't want our timers to start firing immediately. This can be useful if you want to stagger certain animations or want something to happen at a specific time. Although personally I haven't found too much use for that yet. Looking back at the code, you can see that we didn't just give the timer a simple function, but a closure with a defined counter, I. This allows us to keep account of how many animation steps we've taken and make sure to return true once we've drawn all the sightings in this batch. Returning true is how we tell the timer to stop. And don't forget to stop timers or they will continue running forever. If you run the code now, you'll see the animation looks much smoother. There's always something going on, it doesn't feel choppy, and it keeps going and going after the timeline says autumn 2014. Wait, what? The problem is we wanted to give each season a second to render, but as soon as we had more than 60 sightings in a season, it was going to take more than a second. Some have thousands of them, but we've got a basic animation going that's smooth, doesn't take too many resources, and is nice to batteries. In the next video, we're going to look at making it predictably long. We've got a nice smooth animation now. Sightings show up one by one, forever and ever and ever. I've honestly never waited it out, so I'm not sure how long it would take, but a quick calculation says some 40,000 sightings at 60 per second would take just too long. To fix the problem, we're going to change our approach to a delta-based animation. The idea is that if we can figure out how many sightings to draw in every frame, we can make sure a whole season fits into a single second. Except we can't know for certain how many frames will fit into a second. Computers can be slow, frames can take a while, browsers can throttle animations inside inactive tabs, and so on. A lot can happen. But with a bit of math, we can get pretty close. We know from the internet that request animation frame and D3 timer try to give us 60 frames in a second because that's the standard refresh rate of modern monitors. Therefore, we have to render a 60th of our data points in every frame. If we take a delta time between this frame and last frame, we can figure out how many frames have been skipped. We're hoping this number will come out to 1 most of the time. Once we have the number of frames, we can repeat the steps for a single frame as many times as necessary. Suddenly, we can fit varying numbers of data points into a single second. We might be off by a frame or two, but that's not an issue. This approach is going to make our code a bit messier and perhaps harder to understand, but it shouldn't be too bad. First, we calculate how many data points have to fit in a frame. Then we add a previous time inside the D3 timer callback closure. We'll update it every time we render a frame. Inside the draw function, we first calculate the time delta from previous frame, then use it to decide how many virtual frames we have to render right now. And we also have to move the circles drawing stuff into the timer callback. We use .splice to cut as many data points as we need from the head of the positions list, then place them the usual way. At the bottom, we change the counter increment from 1 to the number of points drawn. And we can't forget to update the previous timestamp, which I did at first, and the results were really weird. Running the animation now, it doesn't look as continuous as before, but it does correctly represent the data. Only runs as long as it's supposed to, and doesn't get confused when your browser pauses animations in this tab. Wow, that got pretty complicated towards the end. We went from calling a function once a second to this weird system of figuring out how many frames were dropped and how much we should draw each time we're called to make a reliable animation. But we've learned that request animation is our friend, that D3's timers are pretty cool, and that while messy, delta-based animations are absolutely necessary for anything but the simplest tasks. In the next video, we're going to look at making simple animations using transitions. After all that trouble with timers and keyframe deltas and who knows what else, it's time for something simpler. Transitions. The animations that just work. With transitions, you barely need to think. All you have to do is set an object's start state, begin a transition, define the end state, and, well, that's actually that. That's all there is. These are called twins in the animation industry, or at least they were in my MX Flash days about 10 years ago. In reality, transitions are not much different than timer-based animations. They use interpolators to decide what to change on every frame and calculate how much to change it by. Much like what we dealt with before, just that now it's all hidden from us. To start off, we're going to add a simple fading transition to our sighting points. In theory, this will make them look like a light that turns on and slowly fades away. In practice, it will look better on darker backgrounds and almost unnoticeable on lighter backgrounds, but it will partially hide the sightings to produce a lighter cover, which will help with the next step, adding centroids. We go into drawers.js to poke at the drawing part of the animation loop. Because our points are in a grouping element, it will make the transition perform better. We start a transition with .transition, give it a duration of 800 milliseconds, and define the end state the usual way. In this case, .style for opacity. Transitions work for any set of properties and can be applied to any selection. You can even add transitions to transitions, but those start at the end of the previous transition. Running the animation now, you can see that it looks nicer, and new sightings are easier to distinguish because they seem to pop into view. And you don't run into the issue of everything becoming invisible when more and more sightings are added. Internally, transitions use interpolators to make this happen. They're also used as the basis for D3 scales, and their job is mapping a t parameter from the 0 to 1 domain to whatever range you need. They can even figure out numbers inside strings, complex objects, and so on. You can also make custom interpolators with the attribute twin and style twin functions. One thing to note though is that an element can have only one active transition at a time. You can schedule more, but they have to be staggered with delays or attached to the ends of previous transitions. But as soon as you set a new transition, it cancels all previously occurring transitions. This will be useful in the next section when we're doing transitions in response to user events. Great! We know about transitions and how much easier they are to use than animating them manually with timers. But there's a problem. They don't follow the 12 basic principles of animation. In 1981, Ollie and Johnston published what has since been referred to as the Bible of Animation, The Illusion of Life, Disney Animation. In it, they describe the 12 principles of making great animations. Two of the principles apply to us in particular, squash and stretch, and slow in and slow out. By default, transitions are linear. This is fine for changing opacities, but as soon as you deal with movement or objects changing size, linear transitions feel too mechanic. Too cold, if you will. The solution is easing. It will help us change sizes more naturally and make movement look better with acceleration and deceleration. Now, I've never tried writing an easing function, but luckily we have easings.net. It not only gives us a nice graphic representations of various easing functions, but also provides examples for implementing them in CSS3. Yes, you can do easing and animation in modern browsers with pure CSS. And better yet, D3 supports all of the easings from that example page. We tell transitions which easing function to use by giving it a string descriptor. Let's make our animated visualization more informative by reintroducing centroids. To make it more interesting, they're going to pop bigger when sightings appear in their cluster. We'll do this with an elastic radius transition. But first we have to make the centroids work again. We'll start by adding a centroid class to CSS to make them visually different from the points. They're going to be red and slightly transparent. Next we go into drawers.js and add some extra data to the centroids. We're later going to use it to calculate centroid radiuses and some other things. It's pretty straightforward. Before attaching centroid positions to the SVG, we loop through them and turn them into objects that have the original position and some useful metadata, like the number of sightings in this cluster, the population, and absolute number of sightings. We also set a counter to 0. We'll use this to keep track of how many sightings we've already drawn for this cluster. Next, we have to make 5 small changes to the drawing code. We add a type datum to the main grouping element, change where CX and CY come from, initially set radius to 0, set class as centroid, and add an ID to identify centroids. And if you commented out the centroid drawing code like I did, you have to make sure it's still there. Okay, we've got a visualization full of centroids too small to see. We're going to make them fill up in the sightings animation loop. From now on, we can't just take the loop of the positions array every time we draw something, we have to take the UFOs as well. The easiest way to deal with that is by grouping the two arrays together in a toDraw object. Then we make sure to feed the sightings.data function with toDraw.pos and add some code to select all the centroids we're currently touching. Basically, select all centroids with certain IDs. Now that we know which centroids we're touching, we have to go through each one and increase the counter by the number of sightings we just added to that. To get a count of all currently drawn sightings, we select all centroids again, not just the ones we're updating, and loop through them to make a count. Then we loop through them again to calculate the new ratios. Each ratio is the current number of sightings per capita, normalized by the number of all sightings currently on the map. If there is no population, we assume the ratio is 0 because that makes things easier to draw. When we have the ratios data, we can create a linear scale for the radius. Then we select all centroids again and add a transition with a duration of half a second. We tell it to change the radius to whatever the scale says, and ask the transition to be eased with the elastic in easing function. You can play around with different easing functions, but I think this one produces the nicest looking results. Oh, and before we forget, it's important to sort the centroids and sightings so that centroids always appear on top. We do this by selecting all points on centroids, then giving .sort such a sorting function that all centroids are sorted before other objects. If you run the animation now, you'll see those centroids popping up. They almost look natural, but boy was that a lot of work just to try a line of code related to easing. Anyway, it's been a fun and adventurous section. We've gone from a static map with some circles to an animated symphony of flashing yellow circles and growing red circles. In theory, every frame could stand as its own visualization. We've learned what it takes to manually make an animation with timers and delta-based animations, and we've seen how much easier transitions are to use. We've also talked about using easing functions to make more natural-looking animation. In the next section, we're going to look at user interaction and push our UFO sightings visualization to the next level. We've got a great visualization already, but waiting for a particular year to show up gets pretty boring. In this section, we're going to add some user controls to make our visualization easier to use. We're mostly going to focus on animation controls, but we'll go through some other ideas to make improvements. After we're done, we're going to have an animation that can be sped up, stepped through, jumped through, paused, and even reversed. But first we have to take care of a few holes we dug ourselves into in the last section. Our implementation makes it difficult to fast forward because the timer's approach relies too much on having a set amount of time between frames. We could fix this by just changing time parameters, but it didn't work too well when I tried. There was too much calculation going on and the animation became choppy when you wanted to jump through very quickly. Reversing the animation would also be a major pain. Our current implementation depends on time, which always moves forward. So we're going to take a cue from functional programming and change our animation so it doesn't rely on state. That way we can draw any frame of the animation whenever we want. More importantly, it reduces going forward or backward to just changing a parameter. First, we have to pre-calculate the frames. We're building a data structure that holds the radiuses of centroids and the positions of sightings for each frame. We open the helpers.js file and make a pre-calc animation function. We'll write some new code, but mostly copy-paste the calculation code we've already got. The function will take UFOs by season, geoprojection, and some centroid stuff as parameters. On top, we paste in the season scale definition, define the start year of the animation, and prepare a base state to work from. This will act as our 0th keyframe. The meat of our function is a massive chain of functional invocations. We start by looping through the seasons, keys in UFOs by season, and sorting them. Then we remove all seasons coming before our start year and use a .reduce to make a keyframe for every season and put them together in a massive list. Now you'd normally use .reduce to produce a single value, but with some creative thinking, an array can be a single value as well. In our case, the array is hiding in the .keyframes property of the object returned by .reduce. I'll explain more about this when we look at the make keyframe function. And finally, we go through all the keyframes and add a final bit of calculation, backpropagating sightings to be removed from future keyframes. This will help us run the animation backward. Great, that's the framework done. Now we need to define all those functions. First, we'll create centroid base state. It will produce the initial state of data for all the centroids. We have this code in the drawer centroids right now, so we can just copy-paste it from there. And there's no changes required. Excellent! Next, we'll put the season order function at the bottom of the helpers.js file. It takes 3 arguments, the season scale and the 2 currently compared seasons. We used currying to give it a scale and turn it into a function of 2 parameters. Inside, we rely heavily on D3's .ascending function to sort first by year and then by season if both years are the same. Overall, the function returns -1 if A comes before B, 0 if they're equal, and 1 if A comes after B. Finally, it's time to build the make keyframe function. We'll use the same currying trick to give it some base parameters and turn it into a function .reduce can play with. Now there's going to be a lot going on here, but you'll see it's not too bad. We've gone through most of the code before. .reduce is going to call our function on each iteration with the current accumulated result, the current key, and the current index. Our goal is to add a new keyframe to the accumulated result and return it. The result will be an object with two properties: keyframes, which holds an array of all keyframes, and sum, which holds the state of the animation up to now. A bit difficult to wrap your mind around, but I promise it makes sense. In the function itself, we first use the key to get all UFOs in the current season out of UFOs by season. Then we use group by to go through them and collect a list of cluster IDs that we're going to be touching. We filter out any potentially undefined IDs. Then we have to clone the current sum into a new variable. This is because JavaScript always passes objects by reference, and without making sure to clone the sum, our keyframes would all look the same. With that done, it's time to count all the currently drawn sightings. We do this by adding the sum of all centroid counts in the current total accumulation and the sum of all counts we're about to add. Now we can write the centroid update code from the placeUFOs function in drawers.js. It first updates all the counts and calculates the normalized count per population ratios, then builds a new linear scale and uses it to generate a radius for every centroid. Great! We've got the centroids calculating. Now it's time for the sightings. We can copy the code for calculating positions verbatim, but our life will be easier in the future if we add another .map and give it some more metadata. We give the x and y coordinates proper names and add the cluster and point IDs. Finally, we make an object for UFO data that will hold everything added in this keyframe in the plus property and everything removed in the minus property. We've mentioned the backpropagation of removals earlier. This is where they go. After we make sure to return the result, we're done. Marvelous! We've got a function that pre-calculates all the keyframes in our animation before we even draw anything. Now it's time to write a new drawKeyFrame function in drawers.js. Once again, we are going to borrow heavily from placeUFOs. But the new function will be much dumber. Where placeUFOs had to think about everything from drawing to calculating time deltas and all manner of things, drawKeyFrame will rely exclusively on the data we give it. First, it goes through keyframe.centroids and updates all of the centroids radiuses to the new values. And that's our centroids animated. Bam! Next, we take care of removing any sightings that should be removed. We're certain we're always doing the right thing because we're removing sightings before drawing new ones. That way, anything in the UFOs.minus property can't clash with anything in the UFOs.plus property. We build a selector of all the UFO IDs and remove them. After that, we can just copy the points drawing code from placeUFOs. We have to make some minor changes though. We change the initial SVG select to use a gpoints SVG element, change the data we're feeding it to understand that sightings are now identified by ID, not by index in array, and make sure to give each point its ID. Now we can safely remove the placeUFOs function. It's given us all that it can and is now useless. Almost done. Just some modifications to the centroids function in drawers.js and we're done. Well, pretty much, but the rest happens in the next video. If you remember, we moved a lot of the centroids calculation into those precalc functions. So we start by removing them here because they're no longer needed. We're left with the code that makes a centroid grouping element and draws all the centroids as invisible circles. Now you might remember we used to sort SVG elements on every frame of the animation to make sure centroids have a higher z-index than sightings. That was taking a lot of time and slowing down our animation when there were a lot of elements. So I found a better solution. SVG handles z-index in order of drawing. If we use a layers approach to the drawing, we can get rid of the sorting completely. We draw an empty grouping element before drawing the centroids. This will be our sightings layer, so we're going to fill it later when drawing the sightings. Superb! We've completely revamped our approach to the main animation, simplified a bunch of stuff, and made it possible to jump between frames at will. This way, it won't die even if we want to change a frame tens of times a second. Now the code won't work if you try to run it right now, because we're taking care of that in the next video. We've got the boring part down and it's time to give users all the power. Although honestly, I had a lot of fun figuring out how to do that boring part. Anyway, in this video, we're going to make some animation controls that let users pause, rewind, and fast forward the main animation. We've made our animation easier to control in the previous video. Now we just have to add the user controls to our HTML and wire everything up so it drives our animation. Doing this, we're going to change a lot of code in Code.js. Because we're using Bootstrap, adding and styling the buttons is going to be easy. We open up index.html and wrap the main part in a container div and the graph itself in a row div. This will make sure it renders in the middle of the screen instead of at the left edge. Then we add a new row div and give it a controls class. We'll use this later to have easier access to the buttons. We then divide the controls row into 3 columns, one for controls left of the season, one for the season, and one for the controls right of the season. To make the buttons, we just have to add a button element for each one, give it a bunch of classes, and Bootstrap will handle the rest. Everything from styling the buttons to giving them the right sort of content. We also have to make sure everything's got the right ID or type class. Down, play backward, speed up, and pause on the left, seasons in the middle, pause, play forward, speed up, and up on the right. Now we have to add a bit of CSS to style.css to make things look nicer. We make sure the season indicator is centered and that mousing over it, the user gets a cursor that suggests they should drag left or right. And we add a 20 pixel space between the controls and the graph. The icon flipped CSS class is a bit of a trick. It reverses the x-axis of the play glyph icon to produce a reverse icon. Refreshing the page should give you a bunch of buttons placed neatly under the graph. Now let's go wire everything up in Code.js. We're going to get rid of the stepper and turn it into a new makeStep function. We'll also add a call to precalc animation, which we built in the previous video, and make a simple animation class to drive the buttons. We start with adding a call to precalc animation right after defining the season scale. It needs the UFOs by season, geoprojection, and all the clusters data. Then it returns data for all the keyframes, just like we talked about in the previous video. After that, we instantiate the animation class and the animation variable. We're going to define these later, but we need an instance up here so we can use it in the makeStep function when the timeline hits a limit. Next, we rename stepper into makeStep and remove the call to set interval to leave just the inner closure. We also add a direction argument to the returned function. Now we're going to completely change what this function does. It used to call timeline step with 2 parameters. Now it's going to do everything that timeline step used to do and a tiny bit more. First of all, direction should default to forward, and we need some stops to make sure animation will never go too far back or forward. Checking whether step goes under 0 or beyond the number of keyframes we've got should be enough. When a timeline edge is hit, we want to pause the animation and break out of the function. When that's done, we have to call drawers.drawKeyFrame, also defined in the previous video. Give it the current keyframe and it knows how to handle the rest. At the bottom of the function, we take care of updating the step counter, the current year, and calling updateCaption to update the season indicator. The reason we have to do it differently depending on direction is that we have to make sure the caption always describes the actual state of the graph. We can start the animation right after we've defined makeStep. All we still need is a simple updateCaption function. What it needs to do is use the season scale to get the season and update the HTML in our caption. Simple. Since we're done cannibalizing timeline step, we can remove it. Great. We've done the footwork. Our animation is ready to be user controlled. Time for interactivity. We'll start with a dragging behavior on the caption to make jumping through the animation easier. D3 behaviors are to interactivity what layouts are to drawing. A predefined set of event listeners and default function callbacks that makes it easier to build complex user interactions. The best part is that they define both touch and mouse event listeners, so your visualizations will work great on both computers and mobile devices. D3 ships with only 2 behaviors by default, drag and zoom. Drag is used to make things draggable, and zoom supports zooming and panning. It's usually used for maps. Now to add drag into our caption, we have to first create a new drag behavior using D3 behavior drag and feed it some parameters. It's going to behave better given an origin because it can calculate the delta between original position and current drag distance. Without the origin, everything is sort of jittery and feels like it gets stuck to the mouse. Then we have to do something on the drag event. In our case, we look at the X position of D3 event
and decide whether to explore the timeline into the past or into the future. D3 event X and D3 event Y tell us the current mouse position regarding the captured event, which the drag behavior makes sure is relative to the given origin. The global D3 event object always stores data about the current mouse or touch event. What exactly it holds depends on what you're doing, but it can also keep positions of all the current touches so you can support multi-touch gestures. Finally, we select the caption and call the drag behavior. Now we just need the timeline explore function and dragging is going to work perfectly. It's really simple. Stop any animation that's going on, make a step in the right direction, and that's it. There's just one more thing we want to do before defining the animation class that we've already been relying on. Our buttons need event listeners if you want them to work. You'll see basic intuitivity works much like it does in jQuery and other JavaScript libraries. You select an element and use .on to define a callback for an event. We're only going to add a bunch of click callbacks, but if we want it to be super nice, we should replicate the same callbacks for tap events. Right, we've got everything wired up. All we need is the animation class that drives our controls. We could do without it, but this way it's easier to make sure the buttons always behave correctly. Now normally you could take care of this with AngularJS or one of the other front-end MVC frameworks, but that's a whole other can of worms, so we're doing it manually. We start by defining the function and some internal variables. Player will be our new stepper, playing will be a boolean saying whether the animation is running or not, speed will be the animation speed multiplier, and direction is the current direction of animation. Then we need a toggle controls function that makes sure the right controls are visible in specific states of the animation. We only want pause and speed up buttons to be visible when the animation is playing, and the play buttons only when it's stopped. Plus a bit of logic to make sure left versus right controls behave correctly according to direction of play. After that, we need a start and stop function. Both are very simple. Stop clears the player interval, start sets a new player interval that calls the makeStep function. Speed is used as a multiplier of half a second, which will adjust the apparent speed of animation. We expose the animation API by returning an object full of small functions. Pause stops the animation and toggles the controls. Play forward stops the animation, sets correct speed and direction. Restarts the animation and toggles the controls. Play backward does the same, but sets the opposite direction of play. Speed up first stops the animation, unintuitively reduces the speed, then starts the animation again. Reducing the speed multiplier will make the delay between frames smaller, thus making the animation go faster. Slowdown does the same, but increases the speed multiplier. And voila! Our visualization can be controlled by users. Just run it and you'll see. As you've seen in the last two videos, there's a lot more to making a visualization interactive than just slapping on some events and making elements react to them. Sometimes you have to fundamentally rethink your approach to make the project flow better. In the next video, we're going to add another simple interaction and discuss some ideas for making the visualization even shinier. We've gone through pretty much everything there is to know about user interaction. In this video, we're just going to implement two nice-to-haves and talk about some ideas for what could make this visualization even better. One thing I felt was confusing about our visualization throughout the videos is knowing which sightings contribute to which centroid. That's why we're going to build a simple highlight that draws a shape around all the points in a centroid when you go over it with the mouse. And I think it would be nice if the animation buttons had some tooltips describing what each button does, so we're going to add those as well. Everything about the centroid highlighting will go in drawers.js. In fact, it's all going to fit in the centroids function. First, we add a layer for the highlight shapes between the points and centroids layers. This ensures they will cover the sightings points, but stay under the centroids themselves. Then we add a mouse over and mouse out listener at the bottom of the centroids placing code. The mouse over listener will draw a convex hull around all the points, the mouse out will remove it. We start by collecting all the points belonging to a particular centroid and turning them into a collection of positions. Then we use D3 hull from D3's geometry package to create a convex hull around them. This gives us a collection of points that describe the highlight we're about to draw. It comes back empty if we give it less than 3 vertices, so we break it out if there's nothing to draw. Then we just make a new path on the hull layer, attach the hull points as a datum, and manually draw the correct path using the D parameter. We start a mesh with M, give it a bunch of points denoted with elves, and close it up with a Z. But here's the trick. We first repeat the centroid position for every point, then transition into the correct path using points from the hull. This makes it look like the area grows out of a centroid, which looks nicer than having it just appear. In the mouse out listener, we remove the highlight. There's no transition because it would look awkward when jumping between centroids. And after adding some CSS incantations to style our highlight, we're done. Oh, and we have to make sure our points have those centroid classes. If we refresh now, you'll see that we've got a nice highlight going on. The great thing is, it works even when the animation is running and generally doesn't care about what's going on elsewhere. But it might become choppy in later stages of the animation when your browser is struggling to keep up with all the elements. Now let's take another look at those controls. They look fairly normal. There's a play button that turns into a fast forward button, a pause button appears, there's two sideways arrows that could do just about anything, and a nondescript label that doesn't look like it does much. We can clear up a lot of the confusion with some Bootstrap tooltips. You can use whatever you want, but we're already using Bootstrap to style the buttons anyway, so might as well go for the whole shebang. And we won't even have to go through any trouble. First, we're going to include jQuery and Bootstrap's JavaScript library. We've only had the style so far and haven't needed jQuery because we had D3.js. So we add 2 lines at the bottom of index.html. Then we have to add some tooltip stuff to the controls. Everything needs a title, a data toggle, and a data placement attribute. And after we activate tooltips in Code.js, you'll get a tooltip when your mouse touches any of the controls. Beautiful. There's a bunch more things I wanted to show you, but the interaction section is already long enough. Something I think would look great is using the time of day layout we built in the section on layouts. The way I thought about it was having a mouse over event when you're going on a centroid and replacing it with the time of day display. That way users could see at what time sightings happen most in a particular area. Doing that would entail compiling the correct data, and right now we don't know the time each sighting happens in a particular centroid. Another idea I had was an advanced tooltip that would show you some basic information about each centroid. Things like population, number of sighting, a pie chart of the sightings shapes, and so on. Problem is, I'm not certain where to put it. We could make it float next to the mouse cursor, but that would obscure a large part of the visualization and might look funny. Adding it as an area somewhere to the side could work, but would quickly run out of space on the screen. Another interesting addition might be adding a zoom and pan behavior to the map. That way, users could explore the map and see in more detail where sightings are happening and how centroids are positioned. Adding a basic version of that wouldn't be too difficult, just a matter of using the built-in zoom behavior. But you might want to perform a new clustering on every zoomed-in image so it makes more sense. This would involve a lot of complications. Anyway, all of that might go into a future appendix or a revised version of this video course. But we've covered a lot of ground in this section. We've seen that you can't just slap interaction on an existing visualization. You have to take it into account all the way, or you might have to spend time fixing your code. We've also seen that D3 comes with some built-in behaviors that make our life easier, and that at D3's core, interaction is just a combination of events and animations. Simple. But there's one type of interaction that we absolutely cannot ignore: responsiveness. There are a few things you have to take into account to give a users an awesome experience on mobile as well. We'll look at them in the next video. High-flying interaction ideas from the last video aside, there's one type of interactivity we absolutely must cover: making our visualization responsive. These days, almost 50% of all web traffic happens on mobile devices, and the number is only going to grow. We absolutely have got to take care of mobile users. Right now, our visualization offers a terrible experience on mobile. Not only are we downloading 14 megabytes of data, which is atrocious, we're not responding to viewport size. Our image is a static 960 by 600 pixel behemoth on a small screen, or a tiny speck on a huge 4K screen. Fortunately, we don't have to worry about the big screens because operating systems are smart enough to do some fancy scaling. My Apple screen, for instance, is 2560 by 1600 pixels, and that doesn't break the internet. But it does make images downloaded from the internet look really funny. It wouldn't hurt us to take advantage of having more space though, would it? More importantly, we have to take care of our mobile users. Our visualization is useless to them right now.
Empty space on the left for no reason, image doesn't fit on screen, and God knows what happens if they're tapping on something. First thing we have to do is ask Bootstrap to turn on its responsiveness. Adding a meta viewport tag to the HTML will do. Now, when you refresh in mobile testing mode, you'll see that the unnecessary margin is gone. There's still some funkiness with the buttons and caption, but we're going to leave those alone. There's enough to do with the visualization itself, and I'm sure you can figure out the buttons yourself. Probably just about applying some different Bootstrap classes. Now let's take a few seconds to clean up our code. The animation function does not belong in code.js, and neither do some other functions. They just make it harder to see what's going on. And I like the Boy Scout rule. Always leave code in a better state than you found it. We make a file called animationcontroller.js and move the animation object over there. Then embed the update caption, timeline explorer, and make step functions. We add timeline explorer and make step to the exports and make pause into a callable function because it's used by a few others. We can also move the season scale there as well. Now animation is going to need keyframes and drawers as arguments. And we have to make sure to always call animation.something instead of just timeline explorer. There's 4 cases of that. I'm glad we took care of that. It was really bugging me. Now our job is making sure of 3 things. Make sure the map resizes, make sure data points are in their correct spots, and make sure we draw less data when we have less room. We're going to do all this with a class in the drawers.js file. We'll call it resizer. We instantiate the resizer class with some key parameters on top of the data load callback in code.js. It needs the intended width and height, the data, and the projection stuff. As soon as we got the function, we attached it to the window on resize event. This will call it every time a user resizes their browser, by rotating their phone, for example. To make sure our visualization renders well the first time round, we have to resize it to the current window before we start the animation. Inside the resizer class, we first calculate the aspect ratio and decide that the given width and height are going to be our maximum dimensions. We can also make a simple resize map function. Because D3 geoprojections are magical, it doesn't even have to do much. The geopath function will have been told of the changes, so resize map just needs to reapply it. The resize vis function is going to be more involved because we have to recalculate image dimensions. We start with a temporary width and height. Width is the smaller of full window width or graph container width. This makes sure we take all Bootstrap paddings into account. Height is just the full window height. Then we go through a number of different cases. Each time we set one of the dimensions and calculate the other from our aspect ratio. If the temporary width is smaller than current width, we resize the image to match. If that's not the case, then we check for height being smaller. This takes care of making the visualization smaller when we need it. We take care of making it bigger by checking whether the new width is bigger than the old. If it is, we once more resize everything. But we have to take special care that we didn't accidentally make height too big. We take the same steps if height is bigger. Lastly, we make sure to check whether our new image size is bigger than the maximum dimensions. If it is, we follow the same steps as before. Now when everything's calculated, we set a new width and height property for the SVG element. Then we change the side properties for a geoprojection. We give it a new scale parameter which resizes it, and recenter it with the translate property. Refresh the browser and voila! A scaling map and visualization where all data points stay in the same position. Wonderful! Now let's take care of those data points. This just looks silly. Our approach to moving the data points is going to be twofold. First, we're going to make sure we have longitude and latitude data for everything. Then we're going to use those to calculate positions instead of relying on pre-calculated x and y coordinates. We start in the helpers.js file. In the base positions function, we add lon and lat to the returned properties object. We do the same in make keyframes. Every position object returned should have a longitude and latitude as well. Simple. Now just a couple of simple changes in drawers.js file and we're done. The centroids function should make sure that every centroid has geodata attached. Now because centroids are calculated from point vectors, they don't have geodata natively. We can get it by using the invert function of our projection. Then in the same centroids function, we make sure that our mouse over hulls are calculated correctly. They have to use the geoprojection now. It's a simple fix in the vertices calculation. Just use the projection to get the position. Then, the same fix in the path function as well. We have to map through the given data and feed it through the geoprojection. Simple enough. Fixing the points rendering is just as easy. Find the draw keyframe function and change how we set the x and y positions of the points. All we need now is to update the data points in our resize viscomp function. Turns out it's pretty simple. Select the right objects, set the new property, done. We're just making sure properties are recalculated with the updated geoprojection, and D3 will handle the rest. Marvelous! If you play around now, the resizing would look great. But there's still a problem. When the image is small, all our data points are scrunched together. Not a very useful visualization at all. We can fix this by dynamically changing how many data points we draw as the image resizes. To keep things simple, we're going to remove a random percentage of elements. We start with some max element densities per 1000 square pixels. These numbers roughly correspond with the default densities on our visualization at full size. Then we make a move function for every type of data point in a general move data points function. They're almost identical. The first one is going to be move bases. We calculate the density by counting all bases and dividing by area. If density is higher than our maximum density for bases, we lower the percentage of bases we're going to show. Then we just have to change the moving code. The percentage tells us how many bases to draw before hiding one. We use the iCounter argument to keep track. To hide the current element, we just move it out of view. And we repeat almost the exact same process for the centroids and UFO points. But to make the code perform better, we use the .each iterator instead of repeating the same hiding and moving calculation for both axes separately. After we make sure all three functions are called, we're done. When we play around now, the visualization is never crowded. Sometimes elements that were previously hidden show up at a smaller size and so on, but that's okay. Making this behavior fully correct would take a lot of effort. You couldn't just hide random elements, but would have to make sure to keep the most important ones. But this is good enough to show you the basic idea. And we're done. That's all I wanted to show you with this visualization. We've done a lot, haven't we? Through the last couple of sections, our UFO sightings visualization has progressed from a simple map to a responsive masterpiece with more information than you can shake a stick at. The next two sections are more theoretical, but just as fun. First, we're going to look at some common tools and strategies for debugging JavaScript visualizations, then talk about making our visualization absolutely spectacular. We've already talked a lot about coding standards in the last 6 sections. We talked about reusable components in the section about layouts, mentioned some approaches for making your code easier to understand in the video about functional primitives, and we've done a lot of refactoring and code restructuring throughout. In this video, I want to expand on some of those points, show you how to take your visualization beyond pure D3.js, and talk about debugging D3 code. In 2008, Bob Martin, the author of Clean Code, said that we spend 10 times more time reading code as we do writing it. I'm inclined to agree. As such, I think it's important to make code as readable as possible. The quicker you can figure out what a piece of code is doing, the quicker you can figure out how to fix it, where a bug is coming from, or simply where to make a new addition. So far, we've been making sure all our code follows a certain style, but we never spelled it out. Some of the style I picked up reading various D3.js tutorials and code samples. Some of it comes from my experience fixing other people's JavaScript. The style's basic tenets are: use lots of white space, chain your calls, use narrow code lines, avoid relying on state as much as possible, and functions are better than objects. Let's look at some code from the previous video. As you can see, it's fairly narrow. Including indentation on the left, it's never wider than 80 characters. If you don't count the initial white space, the longest line is only 60 characters, and even that includes a lot of empty space. The 80 character limit might seem arbitrary with modern white screens. I think it stems from punch cards, but it exists for a good reason. Studies have shown that 80 characters is about the maximum length a person can read comfortably without getting confused. And if you look closely, you'll notice that these 16 lines of code form a single expression made up of many statements, each on its own line. We could have chained all this together in a single line, but that would be impossible to reason about. Instead of looking at a line and seeing what happens, we'd have an impenetrable blob of text horrible enough to make a grown man cry. And besides, there's no reason to compress your code manually. We have minifiers for that. Now, without getting into too much detail, minifiers are used in production to make files smaller. They remove whitespace from JavaScript and make variable and function names smaller. The end result is a file that executes as normal but is quicker to download. But if we kept the principle of putting each statement on its own line, why even chain them together? I don't know. For me, it's a style preference, but I think the practice comes from functional languages. In those, the compiler can perform a lot of optimizations with chained function calls because it understands that the operations are working on the same data to produce a unified result. This way, it can avoid storing the data between calls and so on. And even in JavaScript, some of those optimizations do come into play. You can avoid the overhead of instantiating a bunch of variables, and hopefully, sometime in the future, we're going to get laziness and the associated performance improvements. Certain libraries like Lodash and Underscore already do optimize some of those chains. But more importantly, you can see that all these calls are working together to produce a single result. You can tell at a glance that no other part of the code relies on or uses the partial results from this chain. Continuing with the same example, you can see we used a lot of function calls to set dynamic variables, but we never relied on external state. This not only makes code reusable because it's self-contained, but also makes it easier to understand. Each of those tiny functions relies on nothing but the data it is given. If anything funny starts happening, you can just print the data it gets and see why it's doing what it's doing. Problems with D3 visualizations often boil down to data issues. Furthermore, you can be sure that no matter what changes around this code, it will always do the right thing. This means you can move it somewhere else and still be certain it's going to work. Now, of course, there is the small issue of the visualization itself being a sort of state, but that's not too difficult to take into account. And about reusability, strive for it whenever you can. We already spoke about reusability in the Make Your Own D3 layout section, so let's just recap what we've already learned. You don't have to go full out and make a layout every time you write some D3 code though, but you should think about assembling your visualization out of reusable components. You get two benefits. First, you can move your code around at will, change the order of drawing, refactor, things like that. Your code is more flexible. Second, you build a library of components that you can reuse next time you start a project. Why would you spend time writing the same code twice when you can just take some stuff from an older project? Another benefit is that self-contained pieces of code are easier to test and reason about. We'll talk more about this in the next video. In his post, Towards Reusable Charts, Mike Bostock explains how to build reusable visualization components. You start with a simple function, then rather than taking a lot of arguments, you use a closure to bind configuration to your function. This way, users don't have to keep track of both their argument values and your function at the same time. But now you have a function that is configurable only when it's first called. So your next step is to open the closure's internal configuration object to the outside world with getters and setters. To keep convention with the rest of D3.js, getters should be just setters without arguments. Given an argument, change the value. No argument, return the value. And if you always return the whole chart function, your code is now chainable. Magic! The last thing you should take care of is to take the selection as an argument. Do so, and users have a concise way of giving your chart both the target element and the bound data. You can even make sure to react well to changes in the data. We basically did all of this in the layout example, then kinda forgot about reusability. Shame on us. But you should definitely think about visualizations more in terms of reusable components in the future. Another great approach to reusable charts that I've found is using React. Now, I won't go into it here, but if you want to see how that works, you should check out my book React plus D3.js. If you follow these basic principles, your code is going to be awesome and everyone will love you. Make it easy to read, avoid relying on external state, and create reusable components. But things don't always go to plan. Next video is about debugging your D3 code. As much as I would love to, I can't write perfect code the first time around. Coding standards or not, something always goes wrong. Always. Debugging D3.js code can be especially challenging. Code fits together in strange ways, there's a lot of magic going on, and all you have to go by is the misbehaving visualization. But despite its oft magical nature, debugging is where D3.js shines above other libraries. Using SVG gives us the ability to inspect specific elements in the image and play around. We're going to do this in Chrome's developer console, but I'm sure your favorite browser is more than capable of helping you out. I want to show you how to find a subtle bug I had trouble with while making this example. When I was making the visualization, centroids were acting funny. They would always appear in the same spots, but they didn't always have the same sizes. And when moving back and forth through the animation, they wouldn't always behave the same either. For instance, you could travel forward in the visualization, then come back to a particular year, and the centroids would look different than they did when you started. It was really weird. So how do you debug a problem like that? You're not sure if you're imagining things, not sure what the problem could be, but something is definitely funny. First, you have to figure out exactly what's going on. A good place to start is inspecting the visualization elements. Because we're using SVG, we can inspect the element just like normal. If you select an element, Chrome will highlight it and display a small tooltip. It contains the element's full CSS selector and current size. You're shown exactly where in the HTML, or rather SVG structure, the element lies and what its source looks like. This is great when you have to figure out where exactly your element is in the tree, for instance when something is misplaced or children don't inherit events correctly. It usually turns out that what you thought was a child of an element is not actually a child of that element. Anyway, we've now picked an element. To explore its logical properties, we have to switch to the console. Here we can use $0 to refer to the last selected element. Marvelous. Elements hold source again. Now here's a cool feature of D3.js. Because element data is bound to the DOM, we can inspect it whenever we have a reference to the item. Just use the __data__ property. Nothing special in this case, but I promise this is very helpful when you're debugging. More often than not, errors are just a case of data behaving differently than what you assume. Now that you know how to inspect elements, it's time to set some hypotheses. Our problem is that centroid sizes are acting funny. The size of a centroid depends on three variables: the count of drawn UFOs in this centroid, the population in the centroid, the total number of currently drawn UFOs. If these three values behave correctly, the only other explanation is that we're messing up the assignment of a radius to a centroid. But we're pretty sure that's not happening because we're looping through the centroids when calculating their sizes. The easiest variable to confirm is the number of UFOs currently on scene. We can't really know what the number should be for each frame, but it should definitely grow from frame to frame, and it should get pretty big towards the latter frames. Now there might be fancier ways of doing this, but a simple console log will do. In fact, it's my favorite debugging tool. Whenever I don't know what's going on, I just place a bunch of console logs to help me out. Rerunning the code, you can see that the number of all drawn UFOs is rising steadily. Our counting code is correct. We've got two more hypotheses to check. Either the count per centroid is acting funny, or the population is. Now checking the population is going to be tricky at best. It's purely a dataset problem and debugging those can be a beast. So let's look at the count instead. Just like the currently drawn variable, it should be increasing all the time. And on top of that, if we carefully step through the frames, it should grow by the same amount every time. We add a console log to the function and observe. Wrapping it in an if clause will help with the overwhelming number of centroids. And nothing terrible seems to be happening with the count. It increases steadily and we can't know by heart exactly what the numbers are supposed to be. We can add a debugger statement to step through the calculation. It even gives us access to all local variables every time it stops. Perfect. But we've run out of hypotheses. What else could be wrong? Well, we don't really want to check population, and I did end up checking and it was correct. The only suspect we've got left is a new one. Our centroid IDs are getting mixed up. We rely on the ID to make sure UFOs are assigned to the correct centroid, and at one point those IDs come from array indices. A lot of the array manipulation functions we rely on don't strictly ensure ordering is going to stay the same. Because we're using indices as IDs, that could be a problem. Sure, we've been careful to avoid translating between indices and IDs too often, but you never know. If this were a problem, our symptom would be that incorrect points get assigned to specific UFOs. We can check this by going into the console and selecting all points belonging to a specific centroid at different points in time. After a few tries, it's clear that some points assigned to a centroid are actually far away. Now this is going to be a problem, but at least we know what's going on. I'll spare you the details, but after a lot of tracing through the code where UFO data is assembled, you'd find a couple of error points. The filter methods where we get rid of all UFOs with an incalculable position, one in the clustered UFOs function and the other in the UFOs function itself, both in helpers.js. Realistically, every other function we use will maintain the order of elements because it makes no sense to artificially mix them up. But filter takes some elements out and leaves others, which causes confusion. The solution is to perform this filtering only once, in the filter UFOs function. It makes more logical sense anyway. Now, our code works perfectly. Of course, this wasn't the only problem I had with the example code. There were plenty, but this is my basic approach to debugging. Form a hypothesis as to what may be happening, gather as much data as possible, then match your findings to the hypothesis and take them out one by one. Eventually, you will come to the truth. As Sherlock Holmes would say, once you've eliminated the impossible, only the improbable remains. In the next video, we're going to look at some libraries that can help you write even better code. Now that we've covered the work of structuring your code and the pain of debugging, let's talk about avoiding as much work as possible. This video is about giving your visualizations an extra oomph, either by making your life easier with utility libraries or giving you extra features that you don't want to implement yourself. D3.js is great, but as we've seen in this course, sometimes it just doesn't have everything you need. For instance, we used Bootstrap for HTML styling, wireframing, and simple user interactions. We used Lodash for data manipulation, Figure for the clustering algorithm, Moment for time calculations, and FileSaver to create files on the fly. Generally speaking, I'd suggest adding Lodash to every project you're working on. Sure, the new ECMAScript 6 will give us a lot of the utility functions that Lodash provides, but browser support is spotty and Lodash does give us more than ECMAScript 6 ever will. Particularly, we get a lot of list manipulation functions and functional programming primitives that would be annoying to implement from scratch. But don't forget, D3 has got a lot of array utility functions as well. Using a CSS and HTML framework like Bootstrap or Foundation is a good idea as well. It doesn't help much with the visualization itself, but it's always nice when somebody else takes care of the less important things like placing the visualization in the rest of the page. And if you're going to build something big, you might want to consider an MVC framework like Angular or Backbone. It will make handling data changes and adapting visuals to user events easier. Just remember how much boilerplate code went into making animations controls visible only when they're useful. But let's talk about something more interesting: libraries that extend D3.js itself. There are tens, if not hundreds of libraries built on top of D3.js solving various problems. If you pay attention to the internet, not a month goes by without somebody releasing a new graphing library built with D3.js. They usually fall into two categories: D3.js plugins, which are mostly reusable layouts, and graphing libraries that simplify common tasks. You can find most of the plugins in the official D3 plugins repository on GitHub. If you can't find one there, you should bug the author to add it. These are reusable components that you can use in your visualizations, everything from the fisheye effect for two-dimensional layouts to a key binding plugin so you can build keyboard-based interactions. A notable example outside this repository is the D3 Geo plugin, which gives you many more geographic projections than ship with D3. When it comes to graphing suites built on top of D3.js, the landscape is even more varied. As you doubtlessly notice, D3.js is much too powerful for common operations. It only really shines in complex visualizations. But most often you just want a simple graph or a chart, some way to see what your data is doing so it's easier to make a decision. A bar chart or a series of squiggles, stuff like that. Countless people before you have noticed the same thing and took matters into their own hands. I'm not going to show you everything that's out there, but we can go through some of the coolest examples floating about the internet. A recent addition to the landscape is Matrix Graphics. It focuses on giving you reusable visualizations for time series data. I like it particularly because time series are one of the most common and most annoying types of data to visualize. Common because you often want to see what a data point is doing through time, annoying because they're all essentially the same graph. Matrix Graphics gives you a bunch of options for interactions and different styles of graphs. You should check it out. NVD3 is another great library. Less focused than Matrix Graphics, but great for that occasion where you just want a graph and don't really care about the particulars. It can draw most of the basic graphs you can think of, handle all the common interactions, and is pretty easy to learn. And its source is inspired by how D3.js was built. C3.js is a similar attempt at giving you everything you'd usually want to do with D3.js, but with an easier to use API. I haven't really used this one, but it looks pretty cool. I love the name, even if I'm not too big a fan of the default aesthetic they're going for. We can stop here. You get the basic idea. If you need a simple graph, don't build it yourself. Use a library. A while ago, Mike McDermott wrote a great post that collects some of these libraries and the better plugins in a common location. Check it out and see if it gives you any ideas. We haven't covered as much in these sections as we have in others, but that's okay. We looked into some common coding standards and patterns used in D3.js coding, reiterated some of the lessons of the video on functional programming, talked about debugging our visualizations, and looked into avoiding as much work as possible. In the next section, we're going to talk about the design aspect of visualizations. How can we make them work well? Awesome! You know how to make fantastic visualizations. Now that you're an expert, it's your job to make sure visualizations you create aren't only well coded and gorgeous, they have to solve a problem as well. As coders, we often get wrapped up in perfect technical execution. We want our code to look good, work in all browsers, load quickly, be readable by our future self even 2 years from now, and God forbid someone runs a linter on the code and puts us to shame. You do have a JavaScript linter running in your editor, don't you? But we forget about the why. Why are we doing this? Why did somebody ask us to visualize this particular data? Why did the designer want this or that look to our color scheme? You've gone through this course, you know more about data visualization than anyone else on the team. I can almost promise that you do. As an expert, you should know the why as well as the what. Don't be just a code monkey. After weeks of research, I've distilled my hand-wavy approach down to 4 basic questions. Doing this, I leaned heavily on a presentation by Chris W., the lead data science. First, you have to know why you're making a visualization. Sure, they're fun, especially if you're a nerd like me. There's nothing like immersing yourself in some data, finding a snazzy new way of displaying it, and reveling in your magnificent creation when you emerge from the coding cave. But your audience doesn't care about how much fun you had, and your visualization is for them, not you. And just between you and me, they usually want to learn a new insight about something interesting or useful. Once you know why you're making a visualization, you have to know who for. Now this might seem backwards. After all, how are you supposed to know why your audience cares if you don't even know who they are? And it's true to an extent. Different audiences will have different reasons for caring. But the last question was a head fake, as Randy Posh would call it. You should check him out, by the way. His last lecture was brilliant. Anyway, the previous question secretly highlighted why is your data interesting, or what there is to learn, regardless of who is looking at it. I find that thinking about the who muddles the why. But once you know who is your audience, you can think about styling, about appropriate presentation, about the general approach. You wouldn't bore a middle schooler with nitty-gritty details, and you wouldn't offend a statistician by mistaking a median for an average. Those things matter. Great. Now that you know why you're making a visualization and for whom, it's time to think about the data you have to work with. The kind of data you've got is going to dictate the kind of visualization you can make, obviously. Less obviously, it dictates the kind of visualization you should make. HubSpot released a great set of slides about the basics of matching data types to chart types. I'd sum it up as: lines are for trends, bars are for qualitative comparisons, maps are for maps, scatter plots discover trends, and pie charts are usually the wrong choice. Now, of course, there's more to it than that. Whole books have been written about this stuff, and you should check them out. And never be afraid to get new data if you need it. Sometimes what we have isn't enough to fulfill the why and the who. We did a lot of this throughout the course. The last question you should ask yourself is, what do you want? You know the kind of data you have to work with, you know who is your audience, and you know why they care. But it's important to have a personal goal as well. Usually when I think about this question, I change it a bit. Instead of what do I want, I ask myself, what is the one thing I want to change? If there's just one takeaway that my audience is going to have, Just one thing they keep in mind after they leave, the one thing they change about their life or their thought process or whatever. What is it? This gives me focus and makes sure I don't try to pack too much into too little. It doesn't always work, but it's a good aspiration to have. For example, the one thing I want to achieve with this video is for you to think like an expert, not just a shiny things maker. Now I hope you don't think I'm full of talk just because the main example we worked on through the course was kind of a mess. It was semi-carefully chosen as a teaching tool because my audience wanted to learn D3.js, so you cared because you wanted to learn how to make shiny things. You were my audience. Because you wanted to learn, we had to include everything in the kitchen sink. The visualization had to do just about everything possible. The data itself didn't really matter. I chose the UFO sightings because it's an inherently interesting data set. Long history fuels every kid's imagination, and I'm sure every adult secretly longs for the chance to say, "Hey, I saw something weird last night," to their friends. Admit it, we're all nerds here. And finally, I wanted to make something that looks good, is fun to make, and highlights an interesting fact despite being a teaching tool. As it turns out, most sightings happen near Navy and airspace bases. My point is that you should think about the why, not just the what. Your audience will love you for it. In the next video, we're going to look at a few simple ways of going from meh to wow. Now that you know how to make a visualization and why you're making one, it's time we looked at some basic tips for taking a visualization from meh to wow. Or at least from, ooh, shiny, but what am I looking at, to sweet, I learned something. While researching visualizations and visualization design, I found that almost every content mill on the internet has published at least one article about basic design tips for visualizations. Some of them are good, many are pretty bad. The problem is that most of them focus more on infographics and using shiny colors and other useless tips. If you want to have a powerful visualization, it shouldn't just look good. It has to accurately convey the data while highlighting the main story. We forgot to do this with the UFO sightings example because we were too focused on the shiny tech. The best set of guidelines that I've found is N.K. Emery's data visualization checklist. In it, she provides a simple checklist you can use to assess the state of your visualization. She designed it primarily for sociographical use, but many of her points apply across the board. We're only going to look at the most salient points, and I encourage you to read through the real thing on her website. I recently wrote a blog post about my growing spending habits and made my point with a simple graph. I made it with the Numbers app, but that's not important. By default, most spreadsheet apps will make something like this, a bar chart. Now that's not a terrible chart per se. It shows the data and you can see that the bars get bigger every year. Oops. Luckily, Apple's Office suite cares a lot about aesthetics, so this graph doesn't have many of the common flaws. The labels are readable, there's no heavy borders, lines in the background are light, and the color scheme is pleasing to the eye. Not nearly as bad as the sort of graphs scientists use in their presentations. Man, have I seen some terrible graphs in college. If my graph was kinda boring, a graph like this will surely scare you into sleep. And that's the most important rule on the checklist. Only place a pixel or use a color if you know exactly what it's doing there. Avoid borders, legends are evil, and colors should serve a purpose. Okay, so my graph isn't terrible, but it is meh. We can do better. First of all, using a bar chart is wrong in this case. We're not trying to compare absolute values of money spent each year, we're looking for a trend. We could have compared the absolute values, but that's not where the story lies. The story lies in the upwards trend. If you think deeply, when was the last time you weren't looking for a trend in data that involved time? That's right, never. Now humans are pretty smart, so we can see a trend even in a bar chart. But using an area chart or even a line makes trends more apparent. Every brain cycle you spare the audience in interpreting your chart is a cycle less chance they won't even bother. This has to do with how humans process visual information. We're not going to go into all the science here because there's a lot, and I do mean a lot. But Graham Otts posted a great intro article on the topic in April 2014. You should check it out. He talks about how we perceive connections and values from different types of shapes and leans heavily on a seminal book by Jacques Bertrand published in 1967. Yes, it's old. Yes, there's been new development since, but I assure you, people haven't changed that much in 50 years. In the data visualization checklist, Emery captures this concept as a squint test. If you can still see what's going on when you squint at your graph, then it's okay. But my graph could be better still.
Sure, you can see the trend, but it doesn't really tell a story, does it? You have no idea what's going on without reading the accompanying blog post. The quickest way to solve this problem is with a good caption that flat out tells you the point. Don't count on your audience to find a takeaway, just tell them. See, now you can learn the story just by looking at the graph. No matter what happens, no matter where my blog post is reshared, the picture will always tell the most salient part of the story. And that encourages people to read the rest of the post. Now, normally you'd write the caption with a big, easy-to-read font and add a sentence or two describing what's going on. But this was a quick job and I only had numbers to work with. The easiest approach was to just change the legend. No, it wouldn't let me completely remove the legend, which is a shame because it would look better. But we can still do even more. Did you notice those two breaks in the graph? My spending habits make a rapid change between 2012 and 2013. They grow more than linearly in 2014 as well, but that's less obvious. We can make the graph better if we highlight those inflection points. After all, they're key drivers to the story. Now the graph looks as perfect as you can make it in 10 minutes of fiddling with the spreadsheet app. They don't make this step easy. Looking at this, you know the story with or without understanding either of the scales. None of the numbers even matter. Some guys, in this case mine, lifestyle inflates to double its size every year. The biggest change was starting to earn actual money. The second biggest change was becoming financially independent. If he ever gets kids, he's gonna shit his pants. Simple. And that's my last rule. Just tell the story. Yes, writers do have that whole show don't tell dogma, but you're drawing a picture anyway. You're already showing. Tell people what they're looking at as well. And that's it. The 3 rules you can use to make any visualization 10 times better. There are more tips and tricks in the original data visualization checklist, so I encourage you to look it up. You wouldn't do poorly to look at a book or video course that focuses on visualization design either. We don't have time to cover everything here. Now let's get excited about our future projects and look at some of my favorite visualizations in the next video. Woohoo! You've made it to the last video in this course. You're awesome! Not only are you making me happy by finishing, you've learned a whole lot as well. Simply amazing. Now let's revel in some of the amazing visualizations others have made. Best way I know to get cool ideas. Let's start with one of the coolest looking visualizations of 2014. Made by a one-man startup from Prague, it shows a global wind forecast for the next few days. It's a zoomable and panable map that uses a simple flow animation to give you a sense of what the wind is doing. You can even choose different color overlays to get an extra data dimension. There's an overlay for wind speed, air pressure, humidity, and so on. It's really snazzy. But the coolest feature, I think, is that you can look at the data from different altitudes. This gives you a good sense of how mountains and ground obstacles affect the wind. I mean, I always knew they had an effect, but I never realized how big it was. If you look at the map at its highest altitude, all you can see are prevailing winds. It's like the ground doesn't even exist, only wind. Another great feature is that you can click on a particular spot and get a detailed forecast, even including weather and webcams in the area. Windy made this visualization with Leaflet.js, which is a great JavaScript mapping library, and Angular. No D3.js involved this time, but still cool. They say it's meant for people who are into wind sports like kiting and stuff. But fear not, you could make this with D3.js as well. At OpenVisConf 2015 in Boston, Cameron Beccario talked about making Earth, a global wind map. As it turns out, he was actually the first to make this animated vector field effect. There's another great wind visualization among the D3.js examples, which uses circular histograms to show prevailing winds at various weather stations, mostly airports. Nelson Minard divided circles into buckets, filled them with wind data, and out came histograms arranged in a circle. Very imaginative and easy to understand. I love it. Now we used a similar idea to arrange UFO sightings into a clock back in the layouts example. And yes, this visualization is where I got that idea. Another visualization that I have got to mention is everything Hans Rosling has done with his Gapminder Foundation. They started with the wealth and health of nations, then reused the same visualization to show the world a bunch of different population trends. Mike Bostock, the creator of D3.js, made a shiny clone a few years ago to prove that Gapminder's visualization can be made in D3.js. The original is done with Flash for some reason, but this one has all the same features.
The dancing bubbles are countries, the colors represent continents, bubble size is total population, and the axes are income per capita and expected lifespan. Animation time is, well, time. It's a powerful visualization in any respect, but I like it most because it packs 6 dimensions into a 2-dimensional graph, which is just amazing. And just to prove how awesome they are, the people at Gapminder reuse the same visualization for every global population trend they want to highlight. Then they make them into cool videos with Hans Rosling narrating the visualization as it happens. In a recent video called A River of Mist, for instance, they showed that the so-called developing world has essentially caught up with the developed world. There's hardly a difference anymore. You should check out Rosling's talks on YouTube. It's truly an inspiration. And while we're on the topic of world-changing visualizations, I have to mention one of the most famous data visualizations of all time. Jon Snow's cholera map from 1854. He used it to prove that cholera was spread by drinking water, which undoubtedly saved many lives. You see, back in the 19th century, London went through periodic cholera outbreaks that killed a lot of people. But nobody knew what caused them. Some even suggested cholera was spread by smog. So Snow decided to note the deaths of every cholera patient on a map. He produced a sort of spread out histogram of the deaths, where the higher the bar, the more deaths at that house. Doing this, he showed that the closer you go to a particular water pump, the more deaths there are. This suggests that cholera was spread by drinking contaminated water. Revolutionary at the time, but obvious to us. Cholera is spread when sewage comes into our drinking water supply. London built a proper sewage system, cholera outbreak stopped. One of the biggest wins for data visualization. Bam! But we can't finish this list without mentioning the amazing work Mike Bostock did visualizing software algorithms. If I remember correctly, he published a new visualization every couple of weeks and collected them in a giant blog post. Can we still call that a blog post? Anyway, his work is simply amazing. Using D3.js and a couple of paragraphs of text, he can explain even the most complicated of algorithms, or at least the ones most interesting to look at. One of my favorites were the visualizations of labyrinth generation. Labyrinths are a problem I've only ever thought about briefly when given a challenge of coming up with a labyrinth solver in college, but I never considered how difficult they must be to generate. He's also done some magnificent comparisons of sorting algorithms, showed us that shuffling is just as hard as sorting, and gave us some glorious comparisons of image rasterization algorithms. Who knew there were so many ways to turn a picture into a set of colored regions? Most of all, this page and the associated talk shows us that we can use vision to think. I strongly encourage you to check it out. And on that note, I want to finish this course with a quote from the 70s. The greatest power of visualization is showing what we didn't expect to see. Let that one sink in for a bit. But you've come a long way in this course. You started by using and creating D3.js layouts, continued with data processing, graduated to geography, animations, and user interaction, looked at strategies for debugging our code, and finally tried to understand the whys behind the whats. I hope you learned a lot. I know I did. Now go forth and see things.